Okay, hopefully everybody's back in the room. It looks a little bit thinner, but I'd like to stay on time so that we finish on time, because there's nothing worse than being the talk between the audience and lunch, and that's the speaker who's between the audience and the cocktail hour. So it's we're going to welcome Ramon Ferre from the University of Barcelona. I see you're already out there, Ramon, so welcome. You can start sharing your screen and I'll switch over to video mode. You're going to talk about a novel e-health oscillometry approach, a low-cost open source app-driven device. So we eagerly await what you're going to show us as the way of the future. We don't have your presentation mode yet. We just have your slide deck, I think. Perfect. Can you hear me? Ramon, we can't hear you, and I don't see that you're muted, so I'm not sure what's going on here. We are recording. Someone is going to come up here and help me as well. Mute, unmute. Okay. Why would it have changed? We didn't do anything differently. Roger, do you hear Ramon speaking in Barcelona? Okay, well, this was too good to be true. We needed to have a glitch to make this a real conference. I think it may be more. Probably real-time speakers, just in case it's that. This guy. Try it again now, Ramon. No, we don't hear you. So go back to where we were, wherever that was, the one above it. Are we there? Okay. Let's see who's out there. Jeff, if you're there, could you, Jeff Fredberg, could you give us a sound from the virtual platform to see if your mic is working?
Sure. Do you hear me?
Yeah, perfectly well. So Ramon, the issue is on your end.
Yeah, Sandeep here too. So
do we say that again, Ramon?
no, Sandeep here. Sandeep here.
Oh,
so,
Sandeep, hi. No, we can hear you
yeah,
as well.
Yeah.
Ramon, let's see, what are we going to do? Hang on.
Sign off.
Yeah, sign. Okay. So Ramon, if you're going to be around for the next 20 minutes, if Rajoshi is out there from California, we can have her go first, and you sign in, sign out, and then I'll put you a second speaker instead of first speaker. So Rajoshi, are you out there from California? Can you see us and hear us? Because you weren't expected to be here for another 20 minutes. So I think what we'll do is we'll jump into Dave Kaminsky's talk, and we'll let the people on the interweb sort the issues out, and we'll return to you. So Dave's up only for the day, and we eagerly wait. You're going to be sniffing the air, tickling the lungs, and I'll let you do the rest of your introduction because you have the longest talk title of the seminar. Oh, you have
Oh, yeah. No, I no.
I love you.
Yes. It was sweet.
No.
No.
You get to know from
Réponds. Qu'est-ce qu'elle a donc?
I didn't see it here. I'm gonna bring it onto the desktop. Desktop. There it is. Okay, great. Thank you very much. Thanks, Ron, and thanks to all the sponsors of the meeting. It's a wonderful meeting so far, and I've enjoyed it in past years too. And it's a great pleasure to be here. This talk was originally supposed to be given by Sean Wayne, who's one of my fellows doing the project with me, and he's the one who came up with the title. I'm just letting you know. And he's a very clever guy, and he entitled it "Sniffing the Air and Tickling the Lungs: Feasibility of Monitoring the Effects of Indoor Particulate Exposure by Home Oscillometry in Patients with COPD who Heat Their Home with Wood." So it gives you the whole span of what we're going to do. But basically, this is a talk about home oscillometry. This is the map of particulates last night when I looked at the final slide here, putting everything together. This is the United States and Canada. And as you know, here and all over the world, and especially in Greece, Italy, and other parts of Europe, we're under tremendous forest fire problems with air pollution. And if you focus in on the Northeast, which is where we are now, you can see that Montreal, let's see if this mouse works, but we're right here. It had a lot of yellow and one orange spot signifying moderate to severe particulates in the air. And I'm just 2 hours south in Burlington, and we've had a terrible summer too with smoke particulates in our air as well. And that's what we're going to be talking about in this talk, but not outdoor air pollution. Rather, we're going to talk about indoor air pollution. And we're going to talk about particulate matter 2.5 microns in size, so-called PM 2.5. On the left-hand side, you can see that the particles in relation to the human hair are quite small. And by virtue of their size, this makes them quite easy to inhale deep into the lung. As you know, our upper airway filters out particles on the order of 10 to 15 microns and larger. That's why pollen gives us so much trouble during allergy season, because pollen particles are quite large. They stick to our eyes and our nose and our throat and give us a lot of symptoms. But these PM 2.5s and other small particles can penetrate all the way down to the alveolar space. And in fact, there's evidence that they're actually absorbed into the body. So they not only affect lung health, but they can affect cardiovascular health, brain health, and other aspects of biology as well. There was a fundamental study published in 1993 in the New England Journal on the left-hand side that was called Association Between Air Pollution and Mortality in 6 US cities. And you can see the 6 cities designated by letters on the left-hand side with the rate ratio for mortality on the y-axis and the fine particulates in terms of concentration on the x-axis. And as there were more and more particulates in the air, the rate ratio for mortality went up. And S stands for Steubenville, Ohio, a very industrial area of the United States. This study was very important, not only in demonstrating this for the first time epidemiologically, but also it led to the US EPA being sued by the American Lung Association. And this eventually led to the National Ambient Air Quality Standards in the United States. So we know air pollution is really bad for the lungs, and particulates especially are so. Now, particulates can form indoors too. And where I live in the northern part of New England, a lot of people heat their homes with wood. I myself have a pellet stove in my home. That's how I heat my home. Pellet stoves are actually relatively clean, but wood stoves, such as the one depicted here, they have a big door that has to be opened, and you put wood in there, and every time you open the door, particulates can be released into the air. And there have been a number of studies looking at the problem with particulate matter from wood stoves. One in Montana, where they found 50 to 75% of the PM 2.5 in the homes was attributed to wood smoke. And in the UK, they found that the outdoor atmosphere, 21% of the PM 2.5 was attributed to people
having fireplaces at home, wood stoves, and so on, emitting smoke up into the atmosphere. And this was more than the amount of particulates emitted by cars. So it's definitely a big problem. Particulates can be monitored indoors. This is a study from Montana, I believe, that looks at indoor particulate matter. And if you look where the red arrow is, that's showing you the gray line, which is the PM 2.5, and how it varies during the course of the day. It was kind of low, then it spikes up and down. Some of the spikes are related to opening the door of the wood stove. Other spikes are related to opening the door to the outside air, depending on what kind of air pollution day it is out there. We know air pollution is linked to respiratory morbidity in former smokers with COPD, as shown by this study from the Johns Hopkins group. If you look on the graph on the left-hand side, the odds ratio for severe exacerbations of COPD was high in patients who had PM 2.5 levels that were elevated in their main living areas. That's what the circle depicts. The other data in squares was for the bedroom area for two different components, 2.5 on the left and nitrogen dioxide on the right. So we know that indoor air pollution in this way is linked to COPD exacerbations. There was a study that looked at changing out old wood stoves for more modern ones that are cleaner. And if you look at the pre versus post effects in black and white bars, respectively, across many different homes in this study, you can see by and large a substantial reduction in the indoor air pollutants by this measure. So we know we can mitigate this problem by using modern equipment, for example. So in our study, we wanted to see what the sort of prevalence was of indoor air particulate pollution in the northern New England area, especially around Burlington, Vermont, where I live. And the way we were going to do this was to use an indoor particulate matter meter, which is called Purple Air, and it's used internationally. It's a very good meter that measures 2.5. We were going to measure symptoms, and then we were going to measure lung function both by in-home spirometry and in-home oscillometry. And the oscillometer we used is the one that was going to be presented right before my talk. So that was good timing when I saw it on the program, but you'll hear more about that oscillometer next. And this was a feasibility study. I had a small amount of funding from the Northern New England Center for Clinical Trials, which is a local group. We work together with places in Maine as well to do these types of studies. I wanted to see if we could actually make these measurements and what they would look like. So I don't have any fundamental hard data to share with you, but I'm going to show you the kind of data we've collected so far. Now, we're not alone in thinking of this. There was one study out of China that used indoor oscillometry to look at air pollution, and it had some very interesting results. If you look at the graph on the left, the PM 2.5 concentration is on the y-axis, various times of day on the x-axis, and 4 different overnight monitoring periods are shown. And in the blue is the outdoor air pollution. In the red is indoor air pollution, where they gave the households a sham filter system. And in green was an actual filter system. And what they were able to demonstrate was a marked reduction, as you can see, going from red to green by filtering the indoor air to remove some of the particulates. And they related these to different biomarkers using spirometry on the right-hand side, as well as oscillometry. And you can see among the things that changed favorably, impedance and particularly R5 did show a reduction in using sham filtration. So this was encouraging and showing that this was more sensitive as well than just spirometry alone. So we had 3 specific aims in our study. One was to validate the use of the home spirometry, 2 to determine the feasibility of measuring the indoor air quality, and 3 to look at the home oscillometry. We had participants come to an office. We used a rural office down in Barrie, Vermont. Participants came to the office where we made measurements with these devices and instructed them how to use them. Then we sent them home and they did home monitoring for 7 days. Then they came back to the office on day 9 where we collected the devices and made final measurements again. On the left, we used the Go Spiro system. The data could be uploaded to the internet, and we could monitor it nearly real time when patients were doing spirometry. And on the right, we use the oscillometry system there that you can see that Monitored Therapeutics is the company that has a package of the Go Spiro and this oscillometer together. And that was the system that we used. This oscillometer is handheld, as you can see. The participant is given nose clips and a mouth filter. They do not support their cheeks or hand or a floor of mouth. So that's a potential negative of this system. But it does give a broad-based input signal. And then we looked at various questionnaire data, the COPD assessment test, the St. George Respiratory Questionnaire, the MMRC dyspnea scale, and we had the participants keep a diary of symptoms at home. So this was a typical setup when the person came in. You can see I've got the oscillometer on the left with the iPad that would link to it. On the right-hand side, you can see the purple air, the Go Spiro, which happens to be purple. And on the right side near the sink is the purple air monitor, which we mounted on a piece of wood so it would stand. And we asked the participants to put the monitor in the room that they use the most and not right next to their wood stove. So just somewhere where they would be spending a lot of time. These are the kind of spirometry data that we were able to see. You can see the time of measurement in the left-hand column and then the various spirometry measures. This system was very good in terms of quality control. It gave ATS, ERS grading feedback for quality. And then you could actually look at the forced expiratory time, the back extrapolated volume, and the time to peak flow as sort of another check on quality. The oscillometry data also was time-stamped this way. And you can see the measurements. It did do intra-breath measurements. So we got R5 and X5, both on inspiration and expiration. We got R20, AX, and resonant frequency. And these are data from one of the subjects here. And then the purple air monitor was set up, and you could go online, and where it says 20, that was someone in Burlington monitoring their purple air, indoor air quality at the moment I took this snapshot. And that's what all those little circles you saw in the first slide I showed you, that came from purple air monitoring that was occurring all over the United States and Canada. It gave a lot of data. This monitor not only spit out 2.5, but it spit out PM10, PM5, and it gave the current temperature, dew point, pressure, and it was time stamped along the way. So there's lots and lots of data that we had to sort through. We had 8 participants, average age 71. Again, these were patients with COPD. They were all, except for one, former smokers with 46 pack years of history. They had positive CAT and MMRC scores, and their FEV1 as a percent predicted was 65%. Their R5 was slightly elevated at 3.5, and their AX was elevated at 24, just to give you a sense of baseline measurements. Now, the data are very messy. So one thing we've learned from this pilot study is we have a lot more sort of data cleaning to do to try to sort out how to get everything aligned in terms of timing. But I'm showing you the 3 best subjects we had. In the left-hand column, middle column, and right column are 3 separate participants. In the top row are their CAT scores. Second is their MMRC score. Third is their spirometry FEV1. And on the bottom is the PM 2.5. And this is over the 7 days of the study. And if you focus on the bottom first, you can see the PM 2.5s were rising and falling periodically. And we think that has to do with the participants opening up the stove and refilling it with wood and then closing it again, because that's when you would get the most emissions of particulates. The FEV1s kind of bounced around. You can kind of imagine maybe they correlated with some of these 2.5 spikes. The MMRC scores, these are different y-axes for each participant. On the left-hand side, this person had very minimal symptoms. They were scoring 1 every day. The person in the middle scored 3 every day, so they were quite short of breath. And the CAT scores you can see above, and you can see the CAT scores were actually highest for the participant on the right-hand side, where they bounced around, but as high as 24. 40 is the maximum you can get on the COPD assessment test, which signifies the worst symptoms. So yes, we're collecting data. We're not seeing any sort of strong patterns there between the particulates and the symptoms, and the spirometry, hard to say. these are the data from the same patients looking at R5, X5 on inspiration and AX. And I want to help you perhaps stretch your imagination and look at the middle participant. I think the AX might be bouncing around, which is in yellow, in association with the PM 2.5. But statistically, I can't tell you that's for sure. And like I said, we're still analyzing these data. But we are getting daily data. We had them make these measurements twice a day. We asked them to make the measurements somewhere between 6 and 10 a.m. and 6 and 10 p.m. So it was somewhat consistent in terms of time of the day. But they could open and close their stove as they needed to. But meanwhile, we had real-time monitoring throughout the 24-hour period of the particulates. So that sort of didn't matter. And they only took a symptom score once a day. So in summary, I think we showed it's feasible to make the measurements. We still have some work to do with regard to data cleaning and data analysis. One problem we ran into, which was unexpected, is many of the participants did not have sufficient internet access. And so the oscillometer was unable to upload the data real time, even though the spirometer was able to for some reason. So when they came back to the office on day 8, we downloaded all the data from the oscillometer, but it was all time-stamped one day. So we had to go back, knowing they did it twice a day, we had to make our best guesses as to which measurement was which. And so there's some error probably in there. And this was a real hassle to get done. We had we wanted to include primary care sites. And it was all during COVID initially. And then right after COVID, we're still in COVID, in my opinion, but less COVID now. And so it was hard to find participants, that is to say, primary care providers who wanted to be involved. Patients were very happy to be involved, but this took a lot of time and effort to implement. But we're excited about the preliminary findings. And what we hope to do is, in addition to completing the data analysis, 2 main questions. One is, I hope to use these data to help define the prevalence of COPD in the rural Northeast US, and I'll tell you why in a second. And secondly, I'm working with a colleague at Dartmouth, Laura Paulin, who has a lot of experience with indoor air pollution. And she is very interested in trying to use these kinds of measurements in some of her larger multi-site studies. So I hope to help her out with that. And then I'm part of the American Lung Association Indoor Air Quality Initiative, where we're going to be putting together some research grants. So I'm hoping to provide some input on outcome measures such as these for them. And then ideally, it would be nice to use both spirometry or oscillometry to predict exacerbations. I'll talk about that in a second. These are data that were published in the Blue Journal in 2020 on the COPD prevalence in rural and urban regions throughout the United States. And there's one glaring missing entry, which is that red arrow, which is rural Northeast. And when I read this paper, I said, what the heck? That's where I live. And I know there's plenty of COPD. And if you look at the author list, Laura Paulin is in the second grouping of authors there. So I called Laura and said, what's up with this? And she said, we just don't have data. COPD is defined by spirometry, for better or for worse. We know that the definition now extends beyond spirometry, but I'm hoping we might be able to use this approach to better define COPD in rural populations. And then many of you, I'm sure, are familiar with how we might be able to use spirometry or oscillometry data to predict exacerbations. Cindy Thamrin published a lot on this using detrended fluctuation analysis using peak flow. I did a study using peak flow with Cindy's help where we showed something similar in a mathematical way to try to predict when a patient with asthma would exacerbate. And these are data from a COPD trial where they had spirometry data on patients over the course of a year. And here's just one example of someone who had FEV1 tracked in the weeks before and then the weeks after an exacerbation. And you can see the fall in FEV1 is occurring about 3 weeks before the exacerbation. So if we can use these kind of home data to detect lung function, we might be able to develop accurate algorithms to predict when someone's heading towards an exacerbation and hopefully intervene soon so they don't end up in the emergency room or the hospital. So with that, I'll finish. Sean sends his regrets. He couldn't present today because he's working overnight right now. And so he couldn't make it. I've had tremendous help from Caitlin and Olivia, who are in the lung center. And then in addition to Laura Paulin, who I mentioned from Dartmouth, Kelly Cowan is one of our pediatric pulmonologists who's also doing research on indoor air pollution. Thank you so much, and I'm happy to take any questions.
get the gallery view up here, and anybody in the audience here have a question for David while I do this?
I wanted to know if the studies took into consideration whether they were current smokers or former.
You mean our little study?
Yeah.
Yeah, actually, only one was still a current smoker. The rest were all former smokers. Leonard?
Sort of related, maybe not to your study, but I was so curious from the beginning when you started talking about the 2.5 tobacco smoke. What kind of particle size distribution do we have in that? Maybe I should know, but I don't.
Well, I can't tell you the exact distribution, but I know it's wide. In other words, it's 2.5 plus a lot else, and
Yeah.
many toxic gases. as well.
Of course, yes.
Yeah.
But from a particular point of view, would it be fair to assume that if you're a smoker, well, if you have a wood stove, it doesn't really matter much, or would it?
Well, if you're a smoker, you especially don't want further exposure. I
Of
would say.
course, yeah.
Great work, because Joyce and I know how hard it is actually to do home monitoring of pollution. We did a study like years ago. So two questions. One is, what is the major source of fuel, and was that taken into account? Because in our study, what we found was the peaks of air pollution of all the different sizes were all clearly related to actually breakfast and dinner. And we think that that's actually related to the use, it's related to cooking. And in our population, it was primarily because people really weren't using the hoods and the use of gas as a cooking fuel.
So that's a terrific question. We did collect information on what type of stove or oven they have and what the fuel source is, natural gas or electricity, for example. And I haven't looked at those data yet, but you're absolutely right. These fluctuations in PM 2.5 were pretty regular, and they were 2 or 3 times a day. And when we just asked informally how often they refilled their stove, it was usually 2 or 3 times a day. So we're assuming it was from opening the door. And having had a wood stove years ago myself, even if it's a brand new modern one, there's nothing you can do about it. When you open the door, you're going to get some emissions of smoke into the room. But that's a great question.
Then I guess a follow-up is, have you, because I think if I remember the dates right, those are mostly during the springtime and where, if you follow them over the warmer weather, whether, it'll be fascinating to see if you see the same spikes and whether or not those spikes in the AXs
Yes,
also
absolutely.
change.
This was all done in end of February and through March, which was quite snowy and cold still.
Yeah.
And the purpose was because we wanted people using their wood stoves. But you're right, and a nice follow-up study would be the same people out of season for wood stove to see if there's the same exposure. But then the windows are open too, and it's
Wildfires.
the wildfire.
You consider also studying the people living in the same house but not being COPD for the children?
We didn't study others in the home, but we certainly could have. And that would require, just getting a clean filter for each person to do their own measurements and their own questionnaires. But that's a great question.
And another, just because I don't know the field at all, what is a typical time between an insult and then I'm thinking also of fire or something like that, and when you expect to see a result?
That's a terrific question. I mean, people with asthma will tell you that they'll react right away, within minutes, if it's a bad enough exposure. And during the recent smoke in the air, you probably saw this, Ron, too, but I've had plenty of patients tell me they just couldn't go outside that. Even just going out for 5 minutes to collect the mail would be enough to cause a problem. So I wasn't surprised to see, at least in one participant, that AX seemed to be tracking just slightly delayed in time. The particulates, maybe that was a signal, I'm not sure.
There may be also late effects that have a different frequency. So if you would cross-correlate, but taking a wide margin, you can
Absolutely. In asthma, we know there's a late asthmatic response, which occurs hours later. And so that would be something that wouldn't be seen necessarily right away.
Leonard.
So you showed that you could extract the relation exhalation impedance data. Did you have time to analyze that or?
Not yet.
No, okay.
I think there's a couple of questions online. Jeff Fredberg, did you want to?
No. Yes, David, that was just a marvelous talk. Thank you so much. I was going to ask about natural gas, but someone already asked about that. But I'm just wondering, most of the deaths from particulate ultrafine particles are cardiovascular deaths. And actually, Doug Dockery, who's the first author on the paper you cited, he's done a study a few years ago where he showed that in Boston, if you look at people who have implantable defibrillators on the cleanest days versus the dirtiest days in Boston, the defibrillators trigger 4 times more frequently, fourfold, 400%. So I'm just wondering if you thought about looking at cardiovascular events for some of these people who might have pacemakers and implantable defibrillators.
Yeah, thanks, Jeff. Not specifically that, but you're absolutely right about the cardiovascular deaths. And that's what I was referring to when I mentioned that these particles are known to be absorbed in the body and probably have toxic effects, maybe on the basis of free radical oxidative stress, especially in the cardiovascular system and also with brain health as well. But that's a great idea. I mean, if nothing else, we might be able to look at heart rate variability and other markers of cardiovascular health.
Right.
Thank you.
Brian, I see that you're taking time out from the ward at the MUHC where you're currently rounding. Welcome, and what are your thoughts?
Thanks. Thanks for taking my question, and very sorry to not be there. I'm actually just sort of excusing myself from the ward to attend these really interesting talks. Yeah, thanks, Ron. Yeah, so I'm here at NUHC. I'm a COPDologist. I just finished a master's degree in epi, looking at air pollution exposure in COPD in Canadians with pretty mild COPD. And we did find a sort of association between PM2.5 and NO2 in a seasonal manner, and in a delayed sort of lagged manner in COPD exacerbations. One of the questions that I commonly got was, if these patients, say with more moderate or severe COPD, are often housebound, and so the question was often, well, if they're inside their house, does outdoor transient air pollution concentrations matter? So I was just curious, you have a really interesting study set up where you actually have publicly available data for the ambient air pollution concentration and your own sort of household level air pollution monitors. And I was just wondering, now we have forest fires and things like that, but perhaps during COVID, when things were a bit more subtle, were you seeing correlations between indoor and outdoor air pollutions? And if so, how tight of a correlation was that?
So we didn't look for that. During the winter, the air quality was quite good in general. A lot of these homes, I don't know how good their chimney, function was in terms of expelling the smoke high enough and far enough away from the home. One of the problems I know we see in Vermont a lot, and probably other rural areas, is people use these wood burning furnaces that are located a small distance away, 10 or 20 meters away from the home. Then they pipe the hot air into the home, and that smoke itself can be very polluting in the immediate home environment. But the question you ask is a good one, and it gets back to this kind of data I showed you from that Chinese study where they monitored simultaneously the outdoor and the indoor air. That would be a good control to do, and we ultimately do more of these studies. Thank you.
And I almost wonder if an interesting sub-study might be those who are not even using indoor firewood at all, and just sort of seeing how the relation between the outdoor and how that permeates into the indoors and what that means for patients with COPD. Thank you very much.
Yes, absolutely. Thanks.
Okay, well, David, thank you very much. I see Ramon is back. You want to unmute yourself, Ramon, and we'll just give you a test. No, we don't hear you at all. Okay, so we'll get back to you in 20 minutes. And I think, Rajoshi, are you out there and available? If so, please come forward. Oh, there you are.
Yes,
Hi.
I am. Hi.
So welcome. I think we're not sharing here, so you can start sharing. And so Rajoshi is from Cognita Labs, which is, I think, developing the pulmoscan, which we saw in David's talk. So as David said, you're going to tell us more about it, and we look forward to this talk because I saw your talk at ATS. And I specifically asked you to come to Montreal and give it. So I'm really pleased that you're obliging me. Thank you very much and welcome.
Yes, of course. Ron, I just wanted to check first if you're able to see my screen. Is it?
Yeah, we see your slides. And
okay.
speaker view here, so we maximize it. You can begin.
Okay, awesome. Great. Hello, everyone. I'm Rajoshi Biswas. I'm the scientific lead at Cognita Labs and also one of the co-founders. Some of you may know us from our oscillometry device called PulmoScan. And as Ron mentioned, I had presented this data from lung oscillometry for COPD home monitoring back at ADS. And I'll be sharing some of that data today as well, and the potential for improving patient outcomes. It's currently an ongoing study, and it's supported by NIH, UMass Lowell, and Ventura County Medical Center. So here goes some early results from our pilot. So first, let's focus on the current gap in COPD or chronic obstructive pulmonary disease management. We know that patients are at home, especially, are generally unaware of their disease control until it's often too late and they experience sudden onset of flare-ups, often ending up in ER or hospitalization. The resulting cost of this scenario is very high. In fact, just about 100 uncontrolled patients can drive up the cost to over $1 million. But studies have shown that almost 50% of that cost could be avoided through timely intervention. So if we look at the current standard of care at home for COPD, it is driven by symptoms assessment, which is often subjective. And our goal is to detect decline earlier than that standard of care so that we can allow time for interventions. Now, any at-home test that we use, it must be, of course, comfortable to do at home, but also sensitive to airway changes, particularly small airway changes because of COPD. If you think about maybe an overly simplified time of events leading up to an exacerbation, first, it generally starts with physiological changes such as inflammation, mucus buildup in the airways, or alveoli changes in case of emphysema. Which then leads to compromised oxygen exchange and then results in the onset of symptoms. So we know that spirometry may not be sensitive to those early small airway changes, and daily testing is also difficult for a large patient cohort. But when it comes to other sensors such as pulse ox or respiratory rate variables, they may not measure small airway physiological changes and could be late predictors. So we focused on lung oscillometry method, which could be sort of at the intersection of our home monitoring goals. I think most of the audience is already familiar with oscillometry. And one of the reasons for using it for COPD is that it measures small airway function without requiring forced effort so that anyone at home can do the test easily. So for our study, we used the portable PulmoScan oscillometry device, which is FDA cleared for home use as well. And it is an FOT or forced oscillation technique device. It sends multi-frequency sinusoidal vibration into the patient's airways. The output parameters are resistance reactance. But we are also particularly interested in the difference between the expiratory and inspiratory cycle measurement, so the intra-breath analysis given by the device, because we already know that expiratory flow limitation is a known indicator for COPD small airway dysfunction. So we analyze those parameters as well. And we do have some prior literature for home monitoring and exacerbation detection using oscillometry. I've shown some studies here that were recently published, but particularly the study by Zimmerman and team back in 2020, they showed that reactance variability could predict COPD exacerbations about 3 days early. So that was very promising when we were starting out with the study ourselves. And aside from home monitoring, there have been decades of studies that have shown high sensitivity of oscillometry for detecting small airway dysfunction, often earlier than spirometry. So with that early evidence and a home usable device, we partnered with UMass Lowell and VCMC on an NIH-supported pilot study to detect exacerbations from home monitoring data. So the patients that we recruited, they were moderate to severe uncontrolled COPD patients, gold stage 2 and 3, who had at least one exacerbation in the past year. Patients on continuous oxygen were also eligible for the study. Then it was fully remote and purely observational study. So the patients took daily oscillometry tests with the PulmoScan device, and the data automatically sent to our database. They didn't need continuous internet at home. We had a data help to do that job. And then patients also recorded their symptoms by answering standardized CAT questionnaires via simple text messaging. And then we had monthly phone calls from the study staff, not their clinicians, but the study staff, just to note if they had an exacerbation in the prior month and the date and the intensity of the exacerbation. We recorded moderate to severe COPD or exacerbation as something that required prednisone or antibiotic prescription or resulted in an urgent care visit, ER visit, or hospitalization. And till date, and participants and their clinicians, they were both blinded to that data recorded. So we've had about 18 patients who completed the study with 85% compliance with daily testing. And we detected about 15 moderate to severe exacerbation events during the study period. We did provide training to the patients in the beginning of the study on how to perform oscillometry testing. They did 2 tests every day, but we specifically did not focus on quality control during the study to mimic real world usage. You know, for example, current standard guidelines are to do 3 tests, look at coefficient of variation or COV for quality control, but 3 tests every day would be quite a bit of burden on the patients. And we also did not actively monitor the data quality as in a real world use case, but we only contacted patients in case of missing data. So our key result till now is that oscillometry started trending about 5 to 7 days before exacerbation. But let's look first at some of the case studies to see some examples of trends before an exacerbation. And here is a case study from one of the patients where they had an exacerbation, and we have obstruction measured by oscillometry on the top graph and CAT or symptom score on the bottom. And you can see that the symptoms stayed fairly flat until about 1 day before the exacerbation. So this was that sudden onset. But oscillometry, it started trending about 10 days early. So we got like a window of opportunity potentially that could be useful for early intervention to prevent the exacerbation. Next, we have another case study from a patient who had multiple exacerbations. And every single time we do see oscillometry data peaking several days before when symptoms stayed, again, pretty flat. But these are just 2 examples to show early changes. The actual trends would depend on the type of exacerbation. So in some cases, we may see 10-day early physiological changes. In others, it just might be 2-day early change or no change at all. So to get a sense of an average of how the trends were for all the patients, we pooled the data. So we extracted 30-day windows during an ACOPD where we would get 20 days before the exacerbation, 10 days after the event, and then we pooled all those windows together, aligned by the day of the event. We normalized each patient's data so that it's all on the same scale. And here's how it looked for the 15 events combined. Exacerbation is the day 0 line, which is shown by the red dotted line. And we selected baseline as day -20 to day -15. So just before 2 weeks, just 2 weeks before the date of exacerbation. And then we compared each day with that baseline value using Dunnett's multiple comparison test. The change from the baseline is significant if P is less than 0.05. So those are marked in the purple triangles on the graph. So what we saw was that oscillometry data started trending significantly higher than baseline about 5 to 7 days before the event. But for the CAT score, that had a late change, but more importantly, the variability was very high. We think it's likely because CAT score is a subjective measure, but oscillometry is actual physiological measurement. In fact, some patients always rated their symptoms as high, while others rated it as low until the day before the event. So, and this is actually a little similar to prior results that were published by the Zimmerman paper. So I have a snapshot here of that paper where they showed that there was a significant change in oscillometry from baseline about 3 days prior to the ACOPD, but the CAT score was significant only 1 day prior to ACOPD. So there's of course one limitation of our study is that the sample size is small. We are working towards increasing the evidence size. It's an ongoing study. We're also continuing analysis to find a sensitivity, specificity of our data in detecting exacerbations, comparing it with the standard of care or CAT score. So it's an ongoing process, but the early results are promising. So to summarize, we need 2 factors for successful remote monitoring of COPD. First is that the test must be simple enough for patients to do for high compliance. And second is that it must be sensitive to small airway changes. So our pilot study has shown early promise that home oscillometry could be a good candidate. Of course, the key to any RPM or remote monitoring program success is that patients see a value and then they engage and participate in the program. So with this, I'd like to open it up for any questions and answers.
Thank you very much, Josh. That is wonderful data to see. Anybody in the room have some comments or questions? Charlie.
Really interesting study. I wanted to understand better because I'm not sure I caught it. The measurement of small airways disease. What are you using exactly for that? You looking
Sorry,
at minutes of resistance or?
Which oscillometry metric are you plotting as your small airways metric?
Right. So in the case studies, I showed the EX parameter, but for our that average data, the one that shows the average trends, we actually looked at all the parameters. So, you know, oscillometry has a ridiculous number of parameters from resistance at 5 to 30 hertz, reactions at 5 to 30 hertz, inspiratory, expiratory, secondary parameters, breathing, ventilation parameters as well, like tidal volume and all of that. We did the analysis for all of these parameters, found that several of them were trending earlier than exacerbation. We then combined and looked at different combinations of these parameters. And then for the graph that I showed, it's just one of those combinations that gave 7-day early prediction. But we had several of such combinations of inspiratory, expiratory, resistance reactions.
Do you know which one? Because if I'm gunning to see if it's the AX and Charlie's probably gunning to see if it's the frequency dependence of resistance. Do you know which specific one you did show us?
So that the one that I showed you in the, let me just share my screen again.
Just go back.
Yeah, go back.
Yeah. So, all right. See the screen. See.
Sorry, I just want to understand that.
No, I think it's an important question, Charlie.
Of course.
I apologize.
Yes. Let me see. All right. So this particular screen, so this is one of those combinations which has both resistance and reactance parameters. I don't exactly remember the exact combination, but I think it did have reactance components as one. So it could be expiratory phase reactance.
I hope this is not proprietary in a secret cocktail recipe. Maybe what you could do in the future is show us the individual parameters on this graph, because for those of us who work with it every day, that would be much more convincing than having a composite metric, because we're still agreeing on the single metrics as what's most important. We're not ready for composites.
No, honestly, we did this just to see early trends in the data, but we didn't delve deeper into the exact particular combination because this is just to show early trends. What would be helpful is to do the sensitivity and specificity analysis and then find what is the optimal parameter that gives us the best specificity, best sensitivity. So that's the one that would be useful.
I'm actually okay with this.
Okay.
I'll explain why later in the afternoon.
Okay. How much more data have you collected so far? Do you know what your end is at currently? What do we expect for the next meeting?
Yeah.
Next meeting, yeah, hopefully. Yeah, so this we presented in May, so not much change since May. Yeah, but we're trying to recruit patients. Hopefully, our goal is to get in at least to 50 or something, so that we can have a significant cohort of patients in the study. But so far, it is still at 18.
That's great. So unshare your screen, and there's a few more questions from the room I see. So whose hand is going up? Chung Wei.
So I know that you want to represent real world settings, but I wonder if you can give us a little bit of details in terms of how many recordings did you ask each of the individuals to make? And then are you able to go back to the data to actually be able to analyze the coherence and covariance?
Yes, so we asked the patients to do 2 tests back to back once daily, so that we could at least get an average, or if we see an obvious outlier through coherence, we could remove it. We didn't do that in this analysis. We just included all data for now, but we have the ability to go back and look at the coherence values to discard or keep the outliers. But yeah, and I mean, in the future, it would be nice if we could have 3 measurements and do the coefficient of variation, but just practically speaking, this was the most optimal home measurement scenario.
Jeff, did you have a question?
Just a comment that connecting this to the previous talk, the opportunity that oscillometry is apparently providing from previous studies in this study is that there are several days of warning, 2, 3, sometimes even more, depending on the patient, that an exacerbation might be coming. That means you can correlate that with possible insults. We know that pollution exposure might be an insult that actually triggers exacerbation. So if that were true, then you could possibly do an intervention. Knowing that something's rising, you could reduce the insult, perhaps. I think the opportunities in being able to monitor using oscillometry, a predictive event that you might be able to actually intervene in a control versus a control group where you don't, right? Would be as tremendous. So I congratulate you. Good stuff.
Ryan.
Thank you.
Sorry for 2 questions and 2 presentations. I'm trying to get my fill before I go back to the word, but thank you for that excellent presentation. The clinician even in me is convinced that this is really the way of the future, and so it's really exciting stuff. The y-axis of your graph was brought up a couple of questions ago. I'm in fact interested, at least as a clinician, in your x-axis and how you truly define what day 0 of an exacerbation is. In our latest GOLD guidelines, there's the Rome proposal, striving towards being a bit more objective in the way that we define and classify the severity of our exacerbations. But especially in the Wild West outpatient world, I am curious as to how you're going to define what day 0 is, and if you have any opinions on how we should all be defining what day 0 is.
Right. So day 0 of the exacerbation was defined as the date of healthcare utilization. So that would be the date when the patient went to the ER or the urgent care or hospital. Not an office visit, that would be considered, because office visit is not exactly an immediate healthcare utilization. So for moderate to severe, we included those 3. And also for some patients, they were prescribed antibiotics or prednisone remotely through a telehealth consultation. So that was also considered a moderate exacerbation. It would be, I think the definitions for mild AECOPD are still not that well defined. So we are struggling to classify some of the milder episodes. And then once we have a clear definition, I think it'd be good to see combined mild, moderate, severe, how the data changes. Because for several patients, we do see changes before like a cold or continuous flu episode, but they didn't really get prednisone or antibiotics for that episode, but we do see changes. So it would be helpful if we could also get those mild ACPD events in. And then, yeah, but for now, moderate to severe, these are the definitions that we use.
Yeah, it's just tricky when you were trying to bring oscillometry into the clinical sphere, and when you're using the comparator, the gold standard is even not terribly well defined. So it makes it actually extra difficult. Thank you for a great talk.
Yeah. Thank you.
Ramon, I'm going to give you the last word of this talk and the first word of the next talk. So make the segue for us, please.
Can you hear me now?
Very well.
Oh,
Well,
sorry for the inconvenience. I have a technical question for this presentation. Very nice presentation. I have seen from the image that the impedance is measured while the patient is not subjecting the cheeks, himself, herself, or an attendant person. Taking into account the shunting effect of the extrathoracic upper airways, especially if the cheeks are not subjected, I think that this way there is a big dampening of the changes experienced by impedance. And this is not good, I think, for looking at changes along the days. So my question is that true that this device doesn't impose subjecting the cheeks? And if so, what is the reason to do that?
So the main reason for not asking patients to hold their cheeks is just because of the limitations of home monitoring settings where they're holding the device in their hand while doing the test. In the clinic use case, the device does, we do recommend best practices, which is to hold the cheeks. So that then you could have a clinician holding the device and the patient is doing the test with the cheeks on their, with the hands on their cheeks. But because in this home use case, we didn't want to overcomplicate the usage, just hold it, breathe in and out, that's it. Just make it as simple as possible for patients to do unsupervised tests. And then we're also looking at day-to-day changes. So we're assuming that perhaps the shunting effect is fairly constant, but that's an assumption, fairly constant day-to-day for the same patient. And then we look at day-to-day changes due to small airways. So we're hoping that it's not affecting the daily changes for the patient, but of course, if we could find a way to do both, that would be ideal, but just for the home monitoring scenario, we have kept it optional.
Do you agree, Ramon, that they actually are stacking the deck against them? I would think that as the patients worsen and the overall impedance is increasing, they're going to have an increasing amount of energy lost in the upper airway shunt. Whereas if they had rigid cheeks, they might actually be able to get a more robust evaluation than otherwise. So the fact that they're seeing a signal with a suboptimal approach probably heightens its reality. I don't know if you or Zoli want to comment on that. Oh, Zoli, your hand is up, so the answer is yes. What do you think, Zoli? Zoli, you have to unmute yourself. Good.
Yes, I was very pleased to listen to Ramon's comment. All the more I could hear him at last. It's a very, very important point which he raised. It is really ridiculous that devices are shown in the advertisements without correctly showing the needle cheek support. So if the cheeks are not supported, the shunt effect of the upper airway wall changes the reactance values in the first place terribly. So AX could jump up because reactance wouldn't reach resonance frequency at all. So it doesn't work. But along the same lines, I can recall Ramon's work from, I don't know how many years ago, which was about the suggestion of admittance instead of impedance, which in this setting, if we assume that the cheek impedance is the same or the cheek admittance is the same from day to day, then the relative changes could be free from the cheek support issue. Otherwise, from a methodological point of view, the unsupported cheek measurements are absolutely unacceptable by technical standards.
Is there any way we could do a one-handed maneuver? I don't see, I'm tiny on the camera, but I'm squeezing my cheeks with one hand and pretending to hold the pulmoscan with the other. Could the patients
I've done that, yeah. I've done that before, but I think for patients trying to, so one thing is it's remote study, so trying to teach them over Zoom and holding could be difficult, but I mean, again, it was to simplify the process as much as possible. And I also want to add that comment that I do remember Ramon's talk, and and immediately after he said to use the admittance and go back, he encouraged all of us to go back, analyze your data and see if admittance could be helpful. So I remember that we tried it. We didn't see much of a difference actually. So I converted all these parameters back to the 1 by R and 1 divided by X, but I didn't see that much of a difference in the trend. So I'm assuming that either it's not affecting the trends, the day-to-day for our case, but again, we'll probably understand more once we have a larger sample size.
May I raise a very, very final remark on this? It appears to be a very bad habit for manufacturers to shift to this handheld solution. Normally, if you have a stand which is posed against the patient's hands are free for self-support. I don't see the point of this handheld oscillometers at all. Sorry for that.
So again, could you devise a stand for in-home use that would free both hands of the patient? Is a suggestion I'm hearing, which is excellent.
Yes, we do have a stand which we offered to some patients, but due to convenience, they didn't really want to opt for that option. So we sent out some stands, and they preferred to just use it on their own. So we have to look at this because they already have like so many medications they're supposed to take. And then we add an extra test to their daily routine. So they just want to use it, get it over with, and go about their day. And of course, we could have it kept on the stand, but then not everybody would have the physical setup at home. So yeah, it wasn't as practical as we had hoped. We did send them out, but didn't really get used that much.
Yeah, I side with Zoli. Just do it. It'll make your data much better. With that, I guess we'll hand the podium over to Ramon, who's now going to share his screen and his talk. And we look forward to what you have to say.
Hello, can you see my presentation?
Yeah, but not yet in presentation mode. We have your slide deck. You're almost there.
Okay. Perfect. Can you hear me correctly? Okay.
Very well.
So thank you very much. Thank you very much to my previous colleagues to accept to change the time schedule. Well, my presentation is a technical one. It doesn't involve specifically measurement with patients, but is focused, in fact, in trying to facilitate the home monitoring in particular by helping to have devices with relatively low cost. So I will talk about e-health oscillometry approach, which is a low-cost, open-source, app-driven device. This is a collaboration the School of Medicine and the School of Physics of the University of Barcelona, and have no conflict of interest. So we all know oscillometry is useful for assessing respiratory mechanics in a wide range of adult and children lung diseases. In addition to hospital lung function labs, oscillometry is particularly well suited for point-of-care applications, for instance, at the patient home. However, so far, the industry has been focused on commercializing complex standalone devices with relatively high cost. This strategy limits the widespread application of oscillometry in settings where one device should serve just one patient, for instance, home monitoring, or a few patients, for instance, in small core facilities, which is particularly relevant in low and income countries. Contrary to spirometry, oscillometry has not so far evolved to use simplified devices that take full advantage of mobile health technologies. Therefore, we aim to prove that a novel, low-cost, app-driven oscillometry procedure is easily feasible. And most importantly, we disclose all the detailed technical information required for free replication. The setting consists of a health professional device setting. Sorry. And on the patient's side, there is the cell phone application. So the patient uses his or her own application. Sorry, her or him own mobile phone, where an application is uploaded. The cell phone is operated by the end user, either the patient at home or staff in a GP office. And together with the cell phone application, there is, of course, an oscillometry device. But the important point is that this oscillometry device is a slave device controlled by the app, so it can be, as we will see, extremely simplified. To link the patient sector with the health professional device, there is a cloud setting communicated by the internet. The patient, the desk, the health care professional desk operates anywhere, so it can be installed in the personal computer of the hospital, or it can be placed in a mobile phone of the health professional, which is everywhere in the world. In this desktop, the health professional can define a new patient by providing an anonymous identification, and can define the technical measurement data. For instance, how many frequencies to explore, what is the amplitude of these frequencies, what is the phase, etc. So defining the signal of forced oscillation. And then the cloud side receives the storage and sends the measurement parameters and results. The cell phone application is operated by the end user and allows receiving the technical measurement parameters from the manager website, or allows the patient to order the oscillometer device to start measurement, receive the raw pressure and flow data from the oscillometry device, and computes and displays resistance and reactance, repeats measurements as required, and sends resistance and reactance computed, and also the pressure and flow raw data to the manager website. And the oscillometry device, as I mentioned, is a slave device, only with two functions. As required by the app, it applies oscillations and acquires the pressure and flow signals, and sends the acquired pressure and flow signals raw data to the app. The key point of our presentation of our work now is that the codes for setting the manager desktop, for setting the cloud side, and for writing the application, in our example is made, the cloud is based in Azure, which is the cloud side by Microsoft, which is achievable but anywhere, and in most applications is free. Of course, the cloud can be installed in the cloud of the hospital, the university, or in a private cloud, but we have used the Azure one to be more applicable. And regarding the app, we have written the app thinking on mobile phones working on Android. But of course, in principle, it could be also written for iPhone. The point is that in an internet address that we will disclose when the paper is published, we will provide open source free codes. It means that anyone without identification will be able to download all the codes to build the setting. There will be a general folder where the codes and the executables and the codes of the desktop, the mobile app, the cloud, and also the Arduino code controlling the oscillation device. Interestingly, implementing the manager desktop and deploying the cloud setting just takes 30 minutes using the information we will provide freely. And this has to be done only once, just to set the manager desktop and the cloud. And then to download and set each mobile phone to set the app for each new patient just takes 3 minutes. So for any user, using this information would be very simple. The point to mention is about the oscillometry device, which I mentioned has very limited functions. This provides this solution as a low-cost alternative as compared with conventional oscillometry settings, because many expensive functions are carried out without added cost by the already existing patient's mobile phone. So the visual and audio interfacing with the patient, the data processing, the computation of resistance and reactance, and the data transfer to the website is carried out by the mobile phone of the patient. Then the oscillometry device can be extremely simple and cheap. It can be used any alternative that the user wants. This is the conventional setting based on a loudspeaker, a blower for air renewal, a pneumotachograph, a resistance to allow the patient to breathe. And the key point is to use a microcontroller. We use an Arduino, which is a very low chip microcontroller with Bluetooth facility. Here is an example, just an example of the device, the customized device that will be built with a cost of about 100 euros or dollars, more or less the same. And you can see here that is a 3D printed box. And here are the typical device, the resistance, the pneumotachograph. This is a metallic gooseneck to adapt the position of the pneumotachograph to the size of the patient. So regarding the discussion we have in the previous presentation about the need or not to subject the device by the patient him or herself, I think it's very easy to place a device on the table and then just the patient can adapt the position for an easy use. Okay, so I will just show a very simple and resume functioning of the app application. So when the patient has to start, the application in the mobile phone gives an audio message saying, please press the start test button and do not approach to the mouthpiece. Then the device takes the zero correction and makes the calibration. Subsequently, a message appears, now breathe quietly through your mouthpiece while supporting your cheeks. And then the device is providing the oscillation for 20 minutes and recording the pressure and flow data. When this period has finished, automatically the app sends an audio message to the patient saying, please leave the mouthpiece and relax until the next message. And then the results appear. So in that case, the example was set for 3 oscillation frequencies, 5, 11, and 19 hertz. And here it presents the resistance and reactance of the first measurement. Then the audio message tells the patient, the previous test has been processed, please press the start test button again to repeat the measurement. And then this is repeated subsequently 4 times to carry out 4 measurements. If the 4 measurements are consistent, then the application finish. But in case that the app detects an outlier by using the group's algorithm, then it asks an additional 5th measurement. And in that case, at the end, the 5 results appear and the average and standard deviation of resistance and reactance. And then at the end, the app says to the patient, your session has finished. Thank you very much. You may close the app. This regarding the way of working from the point of view of the patient. From the point of view of the manager of the desktop, a few ideas. This is a screen where the health professional creates the pattern of oscillation and sets how many oscillations are, how many frequencies, and then what are the frequencies. In that case, it's difficult to see 5, 11, and 19 with the amplitude that the user wants to compensate for signal to noise ratio, and also the phase. This is for setting the signal for the patient. And then in the manager desktop, the health professional can browse to the list and can, for instance, look at the results of the resistance and reactance, the results with mean and the mean and standard deviation, and also can go to any particular measurement from the patient to have a look to the original pressure and flow data to see or to detect any potential artifact or any way. Very important, the user, the health professional, can download the original data in a Excel type file where, in addition to the results, the raw data of pressure and flow can be downloaded for further analysis. So these data are stored in the manager's desktop and can reprocess it whenever you want, for instance, to recalculate inspiratory and expiratory difference and so on. So this is a very simple device, but allows the user, in that case the health professional, to retain the whole original information for potential further computation. So just to conclude, the general approach presented here and its particular implementation, which can be modified according to specific needs or evolution of the components market, opens a window for more widespread use of oscillometry. It provides a proof of concept of the feasibility of a novel telemetric approach in oscillometry. I think this is interesting to mention that, regardless of similar potential commercial implementation, adopting this low-cost approach is already feasible for clinical services with minor help from university engineering departments. Indeed, by using the detailed codes and instruction we disclose, the setting can be implemented in half an hour by any recently graduated engineer trained in communication technologies. Finally, in particular, our approach may facilitate low-cost point-of-care testing of lung mechanics in network applications, monitoring patients at home, at GP offices, and small urban and rural healthcare centers, both in developed countries and particularly interesting, in my view, in low and middle-income countries. Thank you very much.
Ramon, thank you very much. As you know, I'm a big proponent of home monitoring of lung function. So to see this initiative is very, very exciting. I look forward to accessing your code on GitHub in the very near future. Let's see, I'm going to put you on gallery view and see if anybody here in the audience wants to start off with some questions. Charlie.
Hola, Ramon. How are you? How's the fires in Europe? Can you hear me? Can you hear me? Okay? All right.
Yes.
So I'm having a hard time understanding how you can build an oscillometer with €100 when the cost of the speaker and particularly the power amplifiers to move these things are pretty expensive. So how are you making that magic work?
Well, it's not a magic work. So the device is very simple. All it's a simple amplifier, loudspeaker, and Arduino, and 2 pressure transducers, which you can find pressure transducer of very high quality for $5, $6 each.
No, that part I know, but it's the speaker and the power amplifier for the speaker.
Well, the speaker is a conventional car speaker, okay, and the power amplifier is a simple unit. We describe this in the publication. It's really a very simple component. So I can give you the information, of course, and it will be published.
Okay, thank you. Congratulations, though, on putting this together.
How much
Thank
more
you.
would it cost to go to the full range of frequency and not truncate at 19 hertz?
Well, it's irrelevant. So the user can go to any combination of frequencies because it takes well, at the current development, the sampling frequency is 128 hertz, which means that the maximum frequency is around 50. So in principle, you
Okay, so
can
this is-
select.
This was proof of concept, and you've just shown that you can do it, and then it's up to the person deploying the device or building the device to determine what spectrum they're going to use. In other words, it can be customizable. You could do a mono frequency or a full sweep if you had to, or a full spectrum if you had to.
Yeah. What I mean is that the user can define what are the frequencies to use. Okay. So the time depends on the application. For instance, for monitoring intra-breath differences, perhaps using only one frequency is enough. So that depends on the application, but the system is flexible.
And who is funding your research? Is this something that's university funded? Do you have a grant for this, or is this just like me? It's a hobby and a pastime.
No, this is funded by the own money of the group coming from different sources.
Okay, well, you're to be congratulated, and I'm sure a lot of the industry members here are not very happy with you, but in the interest of the patients, well done.
Now, look, if I might make a comment, I think that this is my personal opinion and probably is wrong, or many people will disagree. But alternative provided by the industry is commercializing devices which are self-contained and are too expensive to be used for home monitoring. It's with the current devices to have an individual device at each patient homes to be monitored. Impossible. And then if one wants to carry out trials involving dozens and dozens of patients at home during months, we need some kind of device which is affordable. This for developed countries. If the forced oscillation can be or wants to be applied in low-income countries or in rural places and rural health centers and so on, I think that cost should be reduced. And this is not, in my opinion, it's not a problem for industry, it's a question of scale. So for an industry, let's imagine any industry, the business can be even bigger, selling 1,000 devices at 200 euros than selling 100 devices at 1,000 euros. So it's a question of scale. And I think that the only way that the physiopathology and clinical community can have to really expand the real life application of oscillometry is to find a way of decreasing the costs. This is my point.
I actually share your view if you look at biomass COPD, which Sandeep, amongst others, has characterized well and educated us about, there are 1 billion people on the planet with obstructive lung disease. So indeed, we need to have a way that can broadly reach all of those people if we're going to deliver healthcare as the way we'd like in the coming decade. Phil, I see you over there. And just to let you know, Phil Dormish, that we are running about 35 minutes late. So we haven't forgotten your talk, but we just, well, it's how we roll up here. It's very casual. Okay, so we're going to move back into the real world and leave the interweb behind for a minute. And Yannick Basset from Laval, I'm very pleased to have him come, I guess, upstream to Montreal. And he's going to give us a talk about smooth muscle in the airways. And I'll let you take it from here. Downloaded it. That's the which smoke talk. No. So I bet you it's here on the desktop. Yeah. this one over here.
Replace.
Here. So. And,
Good thing you're here.
there.
No, but
Oh.
the other one just next to it.
There. And
Oh, thanks, thanks, Ron. Thanks everyone to be here. I told Ron that I will be presenting on mice, and he told me that you guys are species inclusive. So thanks for being that inclusive. I do most of my work on animal model, especially mice. Although I'm using the Tremel tool as well, and works with some clinical clinicians at Quebec at Laval University. So I'm working with mice. It's a different device. A lot of you will still recognize the Flex 7. The advantage of using animal is that the oscillometry can be a lot more precise, and this is and it's just because it's more invasive. And this is Charlie and Jason phenotyping uncertainty principle. As you increase in invasiveness, you increase in precision as well. So we can do things in animal that you just don't have the same precision to do in humans. So I would argue that animal models are very, very important to understand human disease. Ethics committee will also allow you to do things in animal that you're not allowed to in humans. For example, if you want to measure metacholine response in a severe asthmatics, you might not be allowed to do it, or in an asthmatics during a severe exacerbation, they won't allow you to do metacholine challenge, but in animal, you can do metacholine challenge during the acute phase of inflammation. So you can extract information that you cannot otherwise. So I'm using the Flex 7, and in humans, most of the time you're just showing the impedance, or you're looking at resistance at 5 Hertz or reactance at 5 Hertz, or whichever frequency that you like. But in animal work, most of the time it is combined with computational modeling. And one of the model that I'm using is the constant phase model that has been a while for quite a bit. And again, it's extremely precise to predict oscillometric data, and gives you some insights on concrete parameters. What you need to know about the constant phase model, if you're not familiar with it, in mice there's only 3 parameters. You have the one on screen here. This is airway resistance. So that's the resistance to airflow in the conducting airways. And then you have the parameter that describe the mechanics of the lung tissue. So the pressure that you would need to split apart those telescoping canister, or G, which is tissue resistance, and H, that is tissue elastance. So and you can also do the ratio of G over H, and that's a measure that we call hysteresivity, and it's sometimes abbreviated as ETA. So during a metacholine challenge, when rho is increasing, because all of those parameters will be increasing with metacholine, when rho increase, it means airway narrowing. When H is increasing, it means that the lung becomes stiffer. Can become stiffer because tissue can become stiffer, or it can be due to a small airway closure. And then G is also sensitive to closure, but G is also sensitive to small airway narrowing heterogeneity. So when you do the ratio of G over H, this parameter that we call hysteresivity, most of the time it's an indicator of narrowing heterogeneity. In my lab, we're interested, well, at least one of the topic, we're interested to know what is the effect of a sustained smooth muscle contraction on the response to methacholine. So here in these experiments, the mice were split in two groups, one that will be receiving this methacholine challenge. So this is a challenge without tone. It's actually a single dose challenge. So you can see here, it takes 20 minutes. We administered saline at 5-minute intervals, and then a single dose at 100 milligram per ml. And then we look at the change in respiratory mechanics. So at all those parameters that I just talked about, hysterosivity, GH, and growth. And there's another challenge, the challenge with tone. And this is where we look at the effect of a sustained airway smooth muscle contraction on the response to methacholine. So here, if you look at those doses, we have exactly the same cumulative dose. So they sum up at 100 milligram per ml, but the dose was staggered over 20 minutes. So the muscle was activated for 20 minutes, and then we hit with the same final dose. And the hypothesis here was that in the dosing regimen in red, you would have a greater response of the respiratory system than the challenge with in blue. And by the way, my presentation is color coded. So for the rest of the talk, when you see results in blue, it's during the first challenge without tone. And when it's red, it's when we use the challenge with tone. So those are published results. I will walk on, by little faster because I want to show some unpublished results. So here we are looking at this parameter, the G. If you remember the constant phase model, so that's the indicator of lung stiffness. And we're just looking at the first 20 minutes during this period of tone. And as you can see, with saline, there's not much happening. A small increase in age that we see all the time, probably due to stiffening of the lung with accretion of small airway closure. I'm not sure. But then when you had methacholine, every time you had methacholine, you can see a step increase in age. Okay. And I've shown that a few years ago here, and I was arguing that this is due to lung tissue stiffening, but some of you told me that it might also be to progressive closure. So every time you had methacholine, you have some closure. And as long as you don't have deep inspiration, and there's no deep inspiration here throughout the protocol. So as long as there's no deep inspiration and recruitment, you can see the progressive increase in closure. And this is very likely. But then if you look at hysterosivity, this parameter, when you put G over H, you can see those are the same animals measured exactly at the same time, but we're looking at hysterosivity instead of lung stiffness. And you can see that the response is different. It's transient. Every time you had methacholine, you have a rise in hysterosivity, but it turns back to its baseline level before the subsequent dose. And I think this is a set of data that proves, I think, that smooth muscle contraction lead to the stiffness of the lung tissue. Because this imply here, this increase in hysterosivity may be due to airway narrowing heterogeneity, but here it would imply that heterogeneity is waning, is slowly fading while closure is maintained, which I think it's incompatible because you need heterogeneity to get some closure. So I think it's a convincing set of data that proves that the smooth muscle contraction stiffen the lung tissue. It's not just a question of small airway closure. Keep in mind, those are in normal LT mice. So there's no inflammation, there's no excessive mucus, there's no edema. So I think this is a tissue response. Now, if you look at the effect of tone on airway responsiveness to methacholine, you can see, as we published not too long ago, that the challenge with tone actually lead to an increase in the response. And if you want to quantify it, the difference is huge. It's not a small effect, at least in normal mice. So this is published work. Now we wanted to know what is the effect in asthmatic mice. And when I say asthma here, keep in mind this is experimental asthma. Okay, we use a model of asthma, which is, I think, conventional. So it's one daily exposure to house dust mite intranasally for 10 consecutive days. And then we do all our measurement 24 hours after the last exposure. So this is during the acute phase of inflammations. And the only thing that I will be showing here is the response to methacholine. Again, we divide it into two groups, two different challenge, one preceded by tone, one not preceded by tone. So it's exactly the same protocol as we done in naive, except we had to cut the dose by half. Otherwise, the asthmatic mice die. So this is the response of H to the two dosing regimen. So in the control mice, like we show in naive mice, control here is because they've been receiving saline daily for 10 consecutive days. So they do not behave like a naive animal, but they are still our control group here. So you can still see here the potentiating effect of tone on the methacholine response. It's not as obvious as in the naive, but keep in mind that we cut the dose by half. Okay. So we still have this potentiating effect of tone on the response to methacholine. Then when we look in the asthmatic group, now it's completely different. Okay, at first look at the scale. This goes to 300. Here we were at 100. So here you can see like what we call hyper-responsiveness. And the hyper-responsiveness caused by experimental asthma has nothing to do with the hyper-responsiveness caused by tone. Airway hyper-responsiveness caused by experimental asthma is something else. Again, and then if you compare the challenge with or without tone, that there's not much of a difference. You can see that the peak response is roughly the same. If we quantify it, if you put this in the same scale, just to give you an idea, when we use them on the same scale, you can see that hyper-responsiveness caused by experimental asthma is way more pronounced than the one caused by tone. So if you look at the response, if you just calculate the area under the curve, these two curves here, to quantify the response to methacholine, you can see that in the asthmatic mice, you have airway hyper-responsiveness as expected. When you look only in the control animal, if you compare these two lines, the blue and the red, here it's highly significant. It looks small because we put it on the same scale as the asthmatic mice, but all those dots here are higher than these ones, so it's highly significant. But when you compare the methacholine challenge with or without tone in asthmatic groups, you don't see any effect. Okay, so it's not significant here. If there's something, there's a decrease on average. Okay? And there's an interaction that is quite strong. So it means that the effect of tone on the methacholine response depends on whether you test it in healthy animal or if you test it in sick animal. So I'll put back these results on the next slide so we can compare with the other parameters. So this is exactly the same results again. And to us, it was obviously surprising because you have something here, tone, that increased airway responsiveness, and you have experimental asthma here that increased airway responsiveness. But when you put them together, we were expecting a super hyper-responsive mice, but no, that's not what happened at all. So what I think it's happening is that this is a tissue response. Here you have a stiffening of the lung tissue, okay, that is not due to closure, but lung tissue stiffening, whereas hyper-responsiveness in the asthmatic mice is due to closure. But these two things, even if they both increase H, in vivo, they compete against each other. So lung stiffness prevent small airway closure. So I think that's my take on it, but I would be happy to hear your take. Now, as I've done earlier, you can also look at hysterosivity to have an index of closure, because usually hysterosivity, this indicator of airway narrowing heterogeneity, will precede closure. And you can see, if you look at hysterosivity, again, you have hyperresponsiveness caused by asthma. The fact that we're above zero here means that G always increase more than H during a methacholine challenge. This is probably due to airway narrowing heterogeneity. But in both control animal and the asthmatic group, the change in hysterosivity caused by methacholine is smaller in the challenge with tone than without tone. So another sign that heterogeneity is kind of preserved by a sustained muscle activation. So it will go with my hypothesis that here, the fact that you don't have additive effect, it's probably because the stiffening of the lung prevents some of the closure. So finally, when we look at airway resistance, this is, remember, airway narrowing. We have again airway hyperresponsiveness in asthma. Tone do not increase airway narrowing. This is not new. This is something that we published in the past in the naive animal. And when you look at the asthmatics, and this came to our surprise, we actually had a protective effect. So the amount of airway narrowing here was prevented by tone. And it's not a small effect, because if you consider between the two blue, this is what we call airway hyperresponsiveness caused by experimental asthma. Now, if you compare the two red, like they're virtually at the same height. So airway hyperresponsiveness is completely prevented by tone. So the only fair conclusions that we can come up with is the smooth muscle contraction protects against airway hyperresponsiveness and asthma. And I don't want to put too much emphasis on the word protect, because modesty has a way better things. I just want to give credit to the people that have done the work. This work today was mainly from Magali, although Morgan did the discovery initially. I also want to thank all the funding agencies and CIREC, who helps me a lot in most of my work. Thank you.
I think we'll take 5 minutes for discussion, and at 3 o'clock go to the break and be officially quite a bit behind, but still being able to finish on time, paradoxically. So more on that to follow. But who wants to start off with the question for Yanaki? David?
It would be fascinating to do a deep breath at a part of the protocol to see if you can abolish this protective effect, because then that would really narrow it down to the smooth muscle. Because otherwise, maybe methacholine is doing something else.
Yeah.
So maybe, or maybe it's all intraparenchymal smooth muscle, like around the alveolar ducts, and not necessarily around the airways per se, or something like that.
Yeah, I think it's all. Yeah, it's still. I think it's smooth muscle mediated. I don't think there's contractile elements in the parenchyma, even though this has been suggested in the past. Like I think when I say tissue stiffening, I really say lung stiffening and not parenchymal stiffening. You know, there might be a distinction there. Yeah, I think the whole lung becomes stiffer, but it's tissue stiffening because it's due to the airway smooth muscle. But to include the deep inspiration is part of our next mission. Thank you.
Yeah, thank you. This is interesting. Brings me back to my old days. I have a couple of comments, questions here. One thing is that methacholine is a secretagogue.
Yeah.
And that is quite obvious if you ever played around with this useless other Buxco body box, because the poor mice are just sitting there drooling when you expose them to methacholine. So I wonder, how can you separate an effect that you might be inducing over those 20 minutes, if I remember correctly, of a sort of low moderate dose of methacol, the effect of a potential secretions that would then precipitate the big response you see when you then give the big bolus dose, from an effect on the smooth muscle. Because my comment is really going back to Jason's and my old paper where we showed that elastance is almost 100% explainable by de-recruitment of lung units. And we couldn't really find any fraction being depending on anything else.
Yeah, in the case of asthma, I would agree with the most of the response is due to closure, but here we've done exactly the same dosing regimen in LT and LT subjects and sick subjects, and in one case you get a potentiating response, and whereas in the sick animal it has like a protective effect. So like in the control animal, like, because some of the when people were arguing that this is closure, these stepwise increase in G is due to progressive closure, it could have been due to in part like methacholine causing secretions of
I'm not so sure that G has much to do with closure, but H definitely does.
Yeah, that's what I said. I'm sorry.
Okay, all right.
Sorry.
Okay, I hear Mr. Rivity knocking on the internet. Zoli, you want to make your comments, please?
Oh, thank you. It was a very nice presentation and brought a couple of old thoughts back. I can't see why Mr. is still with us, but I have to cite his work. Probably first was a very elegant study in which the constrictor agent, I think it was histamine or methacholine, I don't know which one, was led into the bronchial circulation, so selectively attacking the airway smooth muscle, and the result was the increased rigidity of the lungs. So that was very elegant. And probably your interpretation is similar. So the contraction of the smooth muscle in the bronchial wall, which leads to a moderate bronchoconstriction in terms of airway resistance, gives an enormous increase in the elastance, if I correctly understood it. The other comment was, which is probably fundamentally different from Wayne's interpretation, who called the airway smooth muscle as the appendix of the lung. A totally different thinking. We proved the opposite probably in this presentation. Thank you very much.
Yeah, thank you.
Good. Yeah, really, really interesting study. I'm going to agree with Zoli here that, yeah, I think this begins to sort of bring into doubt what airway smooth muscle is doing here. I mean, it's already been a big conundrum about that. As you recall, in the JP, we all wrote little snippets about what we thought the smooth muscle did in the lung.
Yeah.
Mine, of course, was the correct one, and then it provides support for airways without cartilage by the bone that you've got. You actually have the data to look at it. I mean, if you, in the asthmatic mouse, which I understand was intranasal dust mite, how many doses for how long?
It was once daily for 10 consecutive days.
Okay,
2 milligram per kilogram.
Have you looked at the histology of those?
Yeah, yes.
And is the smooth muscle?
No, there's no changes.
There's no changes.
No. 10 days is not long enough.
No. And if you look at the temporal response of airways, RAW, methacholine.
Yes.
Do you see an enhanced contractility would be expressed by the increased ramp up of airways resistance with time? Or is it actually less?
We see airway hyperresponsiveness. Looking at the change in rho caused by methacholine when you compare naive and asthmatic mice, like you have it airway hyperresponsiveness.
So it is going up.
Yeah, in bulb C. In the black mice.
No, blacks won't do that.
Yeah, but in the white mice, we can see all the parameters that I've been showing you, the four that we use in the constant phase model.
Yeah.
They all go up more in the asthmatics than.
See, what I was thinking is that, airway smooth muscle is not airway smooth muscle, and it's known that it changes its type, goes from contractile to a secreting. And that the antigen might actually be doing that, but if you actually are seeing that, then that sort of obviates that idea.
Yeah.
So then the next would be and I think the correct one, and that's the difference in the amount of secretions that are in the airway and the impact of smooth muscle on.
Yeah, airway hyperresponsiveness. I think it's a misnomer because it's not airway hyperresponsiveness. It's lung hyperresponsiveness, but it's not the smooth muscle that actually constrict more.
I mean, it's all airway closures.
Okay, we'll finish off with Jeff's question.
So a very provocative talk entitled. I want to posit that maybe there could be something, and it's possible that there's something else limiting your maximal response. Like when you're applying tone, you get to this level, and I add more, and I don't see anything more. You call it protective, but it could be that I've reached a limit, either something external in your system because you've got the animal on the flex event, it's forcing oscillations in, and you're limited because of I suppose there's some PEEP added to keep the airways open, right? So there's a certain amount of closure that is being prevented by the device. You may not have hit that limit with the dosing you're done, or you may have hit that limit because I can keep pumping things in, but that device is going to keep airways open. It's still going to push airways in. It's going to asymptote. It's get harder and harder to put more lung in, the more histamine. So it's possible it's external to your system, but it's also possible it's internal to your system, but in a way that I can't really articulate very well. In other words, I am like when I stiffen the airways, I'm constricting against the load, which is the tethering. And if I presume there's no change in the tethering, I'm just going to constrict more within the system, just thinking about it like that. But because of the lung having a nonlinear pressure volume curve, those tethers get harder and harder to pull when I go narrower and narrower. So I will be approaching an internal limit as well. So it's possible that an internal limit that I might be hitting that isn't related to tone per se, but the natural physiology or the external contraption, the flex events and how it operates, that's leaning to your results that you find on that end. It's sort of an analogy that might be easier. If I pour water in a glass to the limit, then I pour more water, I'm not going to get it full. It's full.
Yeah.
Right. So I'm just worried about that as a possible explanation that you might be hit in the mice. In the humans, no, that they have a huge response, and you didn't find exactly the same things, right? So.
Yeah. And air is not a limit. It's actually protecting, right? Like in terms of age, you may think that we have reached a plateau with the experimental asthma, and tone cannot potentiate that further. But when we get into airway narrowing, what we show is that in the asthmatic mice, you actually had a protecting effect of tone. So you might have more airways with multiple pores, but it turns out in vivo in the sick animal, it's protecting against airway narrowing. I think that's what's kind of convincing in the data, but
yeah, I'm saying that your narrowing is being limited from going any further by something you're not in the model. You're not in that equation, the G eta stuff. It's just not in there. And so
I think it's a question of if they all contracted simultaneously, they also inhibit each other from further narrowing.
Yeah, that's a possibility for,
So the lung gets thicker.
and I totally agree with Charlie's point of raising Wayne-Minster's results that stiffening the lung with the bronchial circulation was definitely shown to be like it seemed to be protective in his sense. So it is possible. I'm just positing that there might be another explanation.
Yeah.
Maybe I'm wrong.
Yeah.
So we're 45 minutes over time. We've used, we have 60 minutes of buffer, so it's only going to get worse, but we'll still finish on time. Phil, are you okay with us coming back in 15 minutes? And would you like to do your talk one ahead of schedule, or do you want to do your talk after Deborah's talk? In other words, in 35 minutes?
I'm free whenever for the afternoon. So you can guys keep the normal schedule, and that's totally fine with me.
Okay, perfect. So we'll be back in 15 minutes. In the meantime, you guys chill out on the internet, wherever you are, and we'll see you soon. Bye.
All right, if everyone wants to take their seats, we're going to get started again for the afternoon, final afternoon session.
Yeah, exactly. Very much.
Yeah, how come you didn't want me to?
I wouldn't put.
Oh, so this is me.
I'm not gonna create that.
That's what I'm getting.
Okay, we'll go ahead and get started for the afternoon. My name is not Ron, it is David. But Ron has asked me to moderate this last session to save his voice, so he has plenty of voice for the cocktails and dinner later. I assume you'll need it for that, right, Ron? Okay. And it's my pleasure to introduce our next speaker, Deborah Saeg from Montreal Oscillometry Symposium here to talk about the role of oscillometry in interstitial lung disease. Is she?
Yeah,
There you are. There you go. You're all set to go.
Thank you. So yes, so I'm a respirologist or a pulmonologist, as the Americans like to say, at McGill here. And I got started into oscillometry at Ron's persistent encouragement, I should say. So I'm also an interstitial lung disease specialist. So I'll talk about ILD. That's what I know. And the application of oscillometry in ILD. So I apologize for those who were at the Canadian Thoracic Society meeting. You may have heard some of it, although I did add some new data to discuss. So this project that I will present is sponsored by Boehringer Ingelheim, for which we received an investigator-initiated study grant that was paid to my institution, and I have other disclosures that are unrelated to this talk. So I won't just present the work that I've been doing. I'm also going to talk about the potential advantages of oscillometry in the interstitial lung disease group of diseases. And we're going to spend most of the talk comparing the use of oscillometry to conventional lung function testing, specifically in patients with ILD, and then to discuss future avenues for work and where I think this should be going. So we've heard a lot about airflow obstruction and airways disease today in people, in humans, and in mice. And for those who don't know, interstitial lung diseases are really a group of disorders that affect the parenchyma of the lung, so the lung tissue itself. And it's characterized by often progressive, irreversible scarring or fibrosis of the lung tissue. But it can also be characterized by inflammation of the lung, of the parenchyma, and some of this inflammation may or may not be reversible. If you look at patients' traditional lung function, they're characterized by restrictive physiologic impairment, so reduced lung volume and increased lung recoil. Interstitial lung disease are associated with a shortened survival. The worst of it, the pulmonary fibrosis, is 3 to 5 years from the time of diagnosis. So really devastating kinds of diseases. The problem with ILD is it's complicated and there is a lot of heterogeneity in it. So we know the most about this disease called IPF, or idiopathic pulmonary fibrosis, which is really only one of the different kinds of ILD. And that's really the worst of the ILDs. It has the most scarring, the most fibrosis, the worst prognosis. But there's also a lot of different types of interstitial lung disease. Some of them are autoimmune, some of them are occupational or due to exposures. And so it's hard to study them as a group. What's important also to note is that there can be overlapping airways disease in some of them. So for example, I have an example of a CT scan, coronal images of a CT scan of a patient with idiopathic pulmonary fibrosis. You can see lots of scars, lots of destruction of the lung tissue. And then you can have some patients who have this fibrosis, but they also have superimposed emphysema in the upper parts of the lung. And then these patients may also have a obstructive impairment. And then these patients with sarcoidosis, which is a type of inflammatory disease, can have some more inflammation, but they can also have superimposed airflow obstruction. And then there's a group of disease called hypersensitivity pneumonitis that also is characterized by airway involvement. So there's a lot of heterogeneity. I'm not going to spend too much time on this because you're all very familiar with oscillometry and the pros and cons of traditional lung function. The key here is that in patients with ILD, it's very difficult to do traditional spirometry because it's a forceful maneuver, much more so as the disease gets more severe at the end, closer to their end of their disease. And so oscillometry offers advantages in that it's not effort dependent. So you know this very, very well, like the different measures of what we're measuring with oscillometry. The key here is that because interstitial lung disease and pulmonary fibrosis are scarring of the lung tissue and they're associated with restrictive impairment, you really want to look at the reactance of the respiratory system that's measuring the stiffness. And you would expect in ILD that the stiffness of the lungs of the respiratory system would be increased in patients with ILD. So I looked in the literature for application of oscillometry in ILD, and I found this study that looked at many different lung diseases, including ILD, and they had a big patient population. They had 274 patients with ILD, and they also had healthy control, and they looked at oscillometry and they compared it to these other pulmonary diseases. And the take-home message is that there's a lot of overlap. If you look at just their oscillometry, it's not really going to be helpful to diagnose restrictive impairment due to interstitial lung disease because there's a lot of overlap in your resistance with other kinds of chronic lung disease like bronchiectasis and asthma. And there is also some overlap in the reactance between patients with ILD and also patients with bronchiectasis and asthma and COPD. And so it's not really helpful as a diagnostic tool. So this is my favorite article. I love this one. So it's from Chang-Wei Chao's lab, where they looked at just under 90 patients with IPF from a single center. And they looked at correlating their oscillometry measure, including intra-breath oscillometry with CT scan and lung function measurement. And I just love these curves, these single breath oscillometry curves. I think they're great. And this really illustrates the difference between a healthy patient, a healthy control here at the bottom panel, and a patient with IPF. And you can see here, as I mentioned, that because of the increased stiffness of the respiratory system, that the area of reactance, the area under the curve here is much increased. And even you can see that there's some differences between end inspiration and end expiration in a single breath oscillometry. And so the most important change that they found was that in patients with IPF, there were marked changes in end inspiratory reactance compared to controls. And when they looked at that specific measure, the end inspiratory reactance, and they compared it to disease severity on CT scan, it was the most strongly correlated measure. So it really correlated very strongly with disease severity as measured on scan. And it also correlated very strongly, or the most strongly, with disease severity on lung function testing, on traditional lung function testing like FEV1, FEC, DLCO, and TLC. So I want to talk a little bit about our project with Ron and with Fanny and others. And what we wanted to look at is across a variety of different ILD diagnoses. So not just looking at IPF, but looking at all the patients with ILD. Does oscillometry measure correlate with disease severity as measured by spirometry and diffusion capacity? And then because we have a more heterogeneous cohort, we wanted to look at whether this varies between fibrotic and non-fibrotic ILD. And then after we presented this at the Canadian Respiratory Conference and at ATS, and we got some comment, we wanted to look at whether if you have superimposed airflow obstruction, if that also affects your oscillometry measures. So I'm going to show that. So I'm going to present the results of a cross-sectional observational study where our patients would come to our ILD clinic and they would be included in the study if they had spirometry at the same visit time within the same half day. So all diagnostic subtypes of ILD were included. There were no exclusions. And we also reviewed all their patient CT scans within the plus or minus a year of entry into this cohort to identify those who have a fibrotic type of ILD or those who have a non-fibrotic type of ILD, so more of an inflammatory ILD. We defined airflow obstruction as an FEV1 to FVC ratio of 0.7 for the purpose of this study. All the testing, all the oscillometry testing was done using the TremorFlow. We used some summary statistics to describe the cohort. We compared oscillometry to spirometry using Spearman's correlation, and we compared those with fibrotic and those with non-fibrotic disease using t-test and the non-parametric equivalent called the Wilcoxon rank sum test. And we did the same to compare those with and without airflow obstruction. So these are the details of our cohort. So we had 101 patients. The mean age was 63. We had pretty equal representation between men and women. We had also, I think, not a bad ethnic distribution, which I was happy with. A lot of our patients were ever smoker, a little bit more than half. And then when we look at the diagnoses, very similar to what you find in any other ILD clinic, where about 25% are IPF, about another third have autoimmune disease, and then we have a range of other kinds of diseases. Our patients, if you look at traditional lung function measurement, had mild to moderate restrictive impairment and moderately reduced diffusion capacity. So we looked at correlation specifically of FEV1 and FVC and DLCO. I didn't put DLCO because DLCO did not correlate in any way with any of the oscillometry measures that I'm presenting. The take-home point is that as the ILD disease severity gets worse, so as the FEV1 and FVC drop, then the stiffness of the lung as measured by the area of reactance also increases here, and here. And the resistance at 5 Hz also was tracking. And so very similar to what was shown previously in other studies. When we try to compare between those with fibrotic and non-fibrotic ILD, we really did not find a signal. There really was not any difference in reactance or even in resistance between those with fibrotic and non-fibrotic disease. So really, to me, showing that the actual lung mechanics, the restrictive impairment that you have, it doesn't matter if it's because of fibrosis or if it's because of inflammatory cells in your parenchyma or in your interstitium, it affects your lungs essentially the same way. Your lungs, it affects your oscillometry the same way. So then we separated between those with airflow obstruction and without. I have to say that we only had 12 patients who also had superimposed airflow obstruction as defined by this ratio of less than 0.7. And similarly, there were no significant difference between the groups. I was concerned because there were not normal distribution or measures, as you know, were not normally distributed. So I also did the non-parametric test, but there were no difference in terms of between those with and without superimposed airflow obstruction. So our basically lower FEV1 and FVC are associated with increased reactance and resistance. And I think that we need more studies to really see if it's actually easier for the patients, although the patients report that it is easier. The next step that I want to do, so we're already started doing this, we're already started repeating measures over time in our same patients. So the patients are starting to come back to our clinic and getting repeated tests. So I have not looked at that. We only have a handful of patients that have repeated measures, but I think that'll be really interesting and important. And the next thing I want to do is try to see if oscillometry can detect small changes in lung function over time, and if it is actually more sensitive than spirometry at detecting progression over time, which my hypothesis is that it is. I'm going to skip that. And then people always ask me, is it ready to be used in clinical practice? Is oscillometry and ILD ready to be used in clinical practice? And I think not yet. I think what we need is better longitudinal studies that assess change over time, but also longitudinal studies that will allow us to see how these oscillometric parameters actually correlate with disease outcome and predict disease outcome like progression, exacerbation, death, or lung transplant, which are tremendously important in ILD. It's still not clear to me if the different parameters are different across diagnostic subtypes. Given the heterogeneity, we need a lot of numbers to be able to assess this. And then for industry partner, I think that oscillometry should, we need to start using them in a clinical trial to be able to see how they measure against the clinical outcomes that we're studying. So I think that's it. Thank you very much.
There's plenty of time for questions.
Did I speak too fast?
No.
I was not nervous at all.
Okay,
thank you.
I'd like to start off with a question if anyone else doesn't have one right now. Spirometry is great because we can say there is obstruction or not based on the FEV1 FVC ratio, and then we can hint at restriction based on the FVC in relation to that ratio. But right now, there's no way to use oscillometry that way. However, I've been thinking about this for a while. The thing that's different is if you correct the lung volume like we do in the body box and we use specific airway conductance, in patients with obstructive lung disease, that value is often abnormal. If we could somehow correct the lung volume with oscillometry, then I imagine we might see a discordance between the airway resistance and the reactance in interstitial disease versus the airway resistance and reactance in obstructive disease. Is that something that you have body box data, for example, that you could use concomitantly with this to somehow adjust your lung volume?
Yeah, so you would be using plethysmography to measure the lung volume.
Right.
Yeah, rather than gas dilution, you would use plethysmography.
Yeah.
So we do have some data. I would say about a third of our patients also have body box data on the same test. The problem is at our clinic, we don't always do full PFTs. We often do just sometimes spirometry. So I'm not, as I'm sure as everywhere does the same. So I'm missing a lot of this, the total lung capacity as measured by plethysmography in these patients. But I think that's really interesting. I do have a subset of patients who have that, and I think it would be really interesting to look at.
You do have scans of that.
I do have CT scans on all of them. Yeah. So then how accurate is lung volume measurement on CT scan,
Well, yeah, but Charlie, the problem is that you have positional difference and superimposed fibrotic as well.
Well, I think the biggest problem is going to be if the CT was not shot at true TLC. In other words,
I agree with that. Yeah.
The tech didn't say, and you don't monitor that typically.
So there are ways around it. If you measure tracheal diameter, if you look at the trachea, to make sure there's no posterior wall, the posterior wall is not coming into your trachea. So there are ways around that, but you're right, because we don't protocol necessarily these patients for research, these CT scans for research, where we can actually really monitor that the CT scan is protocoled properly. And a lot of these CT scans are not necessarily done at our institution. Some of these patients come with their CT scan from another institution to my clinic. So, but that's in those patients in whom I have body box measurement, I think that's a really good idea.
No, then I was just thinking about the VA that you have from the diffusion test. So some kind of.
Oh, that's a good point.
Yeah.
I couldn't hear somebody's
If the FEV1 ratio is normal, the alveolar volume from the diffusion test becomes a decent surrogate.
Yes.
You could use that.
Yes and no. You have to have, so in some diseases where you have a lot of superimposed airway trapping, you have mosaic, it's less applicable, but in IPF in general it is. Yes, that's a good thought.
Yeah.
David, are you?
One thing that we did in mice many years ago in a sort of mixed disease, I think Charlie and David might remember this, was that I started doing what I call the PEEP trial. So I just did oscillometry at different lung volumes essentially. And that actually showed, that's the trick to get the signal out of the restricted animals, because otherwise they looked pretty normal. Because it's like inflating a bag. If the bag has a lot of flexibility, you can go big. But if it's more like a paper bag, it will reach a finite volume, and then everything goes into gas compression instead. And that's when you see that the restricted animals actually have a true restriction. So a trick, I haven't tried this in humans, but well, Jason, I did it once or twice maybe, but that would be to have the patient do a very simple maneuver. That would be starting from FRC and then take a breath until they're into PLC essentially, and oscillate throughout the whole epoch. We could do it vice versa, start from full lung and then slowly exhale. And then look at how the impedance varies over this trajectory. Of course, it's not a standard application in any of the devices, but certainly something one could think of.
Yeah, that's worth.
Can I make?
Not Deborah.
No, I see you out here.
I don't know if you guys are taking comments from the audience or not,
Yes.
but
Yes, please.
Not from you.
No.
oh, shush.
If you couldn't make it up here in person,
Yeah.
All right, I'll lower my hand then. So I wanted to, you know, first of all, I'll make two comments. The first that you just said, David, is very, very important in relating the resistance to the volume at which you're measuring things is very important, and calculating conductances is one of the things that I would encourage, particularly in patients with ILD that have FRCs that are very, very different, right? And the lung size at which you're calculating the resistance, it ends up being very important. We actually did do the experiment that was just proposed in ILD and OLD patients, not only in ILD. Because at the end of the day, you know, you have impedance measurements that are abnormal in both subjects, and you can't really distinguish why the impedance is abnormal in both. And they behave dichotomously. And we looked at this with Jason, and I asked him to model this. We have about probably 30 patients in both groups. We haven't gotten down to writing this, but I encourage you to give it a shot. And what you will see is that when you compare lungs that are measured at different lung volumes in different disease states, you will uncover the reason by which the impedance is abnormal. And in patients with ILD, you'll realize that taking them up, not to TLT, but just a little below, to about 80% TLC, things flourish and impedance goes wild. Resistance measurements don't really change, but the reactance spectrum significantly worsens. And in patients with ILD, it's completely the opposite and dichotomous. When you inflate somebody, resistance comes down really nicely, heterogeneous, the lung becomes less heterogeneous. And actually, there are very small changes or minimal changes in the reactance spectrum. So if you compare those two, you probe the lung, you uncover the reasons or normalize the reasons for impedance abnormalities, you'll see wonderful things, and I encourage you to take a look at it if you have new patients coming in, because that's when your signals will magnify drastically.
Great, thank you. That's really interesting.
Comment and a question. The comment is, I agree. I think Chung Wei's in Toronto's comments is equally seen less now at Imperial College. I see it in my own practice. And that's that disjoint between the resistance curve, relatively preserved, and the reactance curve, which at least under resting tidal conditions, is sort of at best modestly perturbated and not worse than that. And when it's worse than that, or when there's a frequency-dependent resistance, in my practice, they all have overlap. And they have COPD as well, which gets me into my question, is 3% is what your combined lung fibrosis and emphysema was, which I found extraordinarily low, because in my own practice, it's way more prevalent than that. And I'm wondering, are they hiding over with Jean Bourbeau and Brian Ross in the COPD
Well-
clinic, and they just haven't recognized the IL for them over to you?
I think it depends on which ILD you're looking at. Like, you know, if you look at 3 patients out of 25 IPF, that's about that. That's about 10%, right? So if you look at 3 patients out of, you know, like all these patients with scleroderma and rheumatoid arthritis and whatever and HP, then they don't really have necessarily the combined fibrosis and emphysema. So I think it depends on your patient population.
You know, mine is very different from yours because it's new practice, so I'm talking level, but I still would expect you to have a little bit more. And I think Chung Wei at University of Toronto, you had more of the overlap than 3%, did you?
We do, but I have to say that we were specifically targeting IPF, so we weren't at all that. So they were sort of punted from our initial sort of, and most of the patients who had combined were people who sort of slipped through the initial screening. So I mean, so I don't think that our group is very representative. And if I may add, you know, I think it was great data, but I think you may have undersold yourself a little bit, because when I saw your fibrotic and non-fibrotic disease, there was clearly a signal in terms of the X5, right? So
Or X5,
Yeah, my X5, yeah. So we'll have to talk over dinner and see how we can.
We have time for one more.
Yeah, so I was running the lab back in the days when Schwartz and King were putting together cohorts, but we measured everything under the sun as they came through, including pressure volume curves. So what that allowed us to do is calculate upstream resistance. And I always thought that a restrictive patient would have these high pressures and low lung volumes and such super flow rates. They don't. That's rare. They all have mixed disease, and I wondered why that was until you start looking at the histology. The airways are all involved. There's clear pathology there. So I think that it's rare to see a patient who has what you might call pure restriction. And Benno is right. I mean, you get these, we were doing coefficient of refraction, which is the measurement of pressures in TLC, and the curves go up and then they get really stiff as you approach TLC. I think your data, these data from this groups of patients, raise into question some of the language. From oscillometry, we talk about lung elastance. We're not looking at the elastance. We're looking at the volume of the lung. And as the lung gets smaller, it gets apparently stiff. But it's not intrinsically from a tissue point of view stiff. And I think Jason was showing that with his modeling this morning. I think the data that you guys are presenting. So I think we have to revisit how we refer to XR, X5. What is that? I don't think the lung elastance is a great term, because that's going to cause confusion, right? You would have expected these really high and deep ones.
All right,
Right.
great.
Thank you
so much. Okay, our next speaker is Phil Dormish, who has been waiting very patiently, I understand, from a long time ago. So Phil, I'm going to make sure you can share your screen with us. And you should be able to share it now. And you'll have to come off mute. There you go.
Thank you. I'm working on getting the screen set up for us. If we get this guy to work. All right. Everybody see my slides?
It's come up now, and let me just put it on the full view here. Or I think you have to do that. If you can click on the full slide view. Beautiful. You're all set.
There we go. Awesome. Thank you guys. My name is Phil Dormish. I'm one of the pulmonary fellows working at NYU with Benno and Roberta, working in the Andre Cournand Pulmonary Physiology Laboratory. I really appreciate the opportunity to be here today with everybody. I'll start off by saying I've got no disclosures for the day, but I will be talking about differing respiratory mechanics uncovered by oscillometry in patients with COPD. So COPD reflects a mixture of a couple of different things. We've got both airway disease as well as parenchymal destruction. When we think about airway disease, this is leading to potentially more of a chronic bronchitis phenotype. We've got increased resistance that's really due to airway narrowing. When we're thinking more about the parenchymal destruction, this is producing more of an emphysema phenotype. We've lost our lung recoil. And it's really important as we think about this to differentiate those phenotypes as we're thinking about both therapeutic and prognostic kind of points for these patients. And Timmons et al. Had mentioned this back in their paper in 2012. And given the difficulties of using traditional pulmonary function tests, such as spirometry and lung volumes, which really can't differentiate these two different phenotypes, they proposed and started to work through using an exploratory flow limitation with oscillometry to try to identify those different phenotypes to figure out how we can better treat those patients going forward. Now, this idea of using oscillometry to identify our phenotypes was taken a little bit further by a couple of other groups, which I'll talk about here. So Krim et al. They used the Eclipse trial, which was a 3-year longitudinal study, which was really aimed to try to define those COPD subtypes and identify any parameters that could predict disease progression in those subtypes. They had access to biomarkers, imaging, spirometry, oscillometric data. One of the interesting things that they point out in their paper is that there was a subset of severe COPD patients with normal oscillometric parameters that they thought may represent a distinct clinical subtype. When they looked at those COPD patients as a whole, their oscillometry is abnormal. But there's a range of patients going anywhere from about 29% to low 80s percent, depending on the oscillometric parameter, that actually had normal oscillometric findings. And they didn't have a clear explanation of why that might be going on. This idea of developing the phenotypes was taken a little bit further by Wada et al. In 2018 in their paper, which was looking at the diversity of respiratory impedance based on quantitative CT in patients with COPD. They were trying to take imaging findings, how much either airway wall thickening to represent more of that chronic bronchitis phenotype, or kind of a low area attenuation to represent more of the emphysema. And they were able to identify that the oscillometric parameters showed significant correlation with the degree of airway wall thickness. Interestingly, however, there was no significant correlation that they had between those oscillometric measures and the degree of emphysema. It seems like there's kind of been a start of being able to use oscillometry to start to identify these different phenotypes. So taking this data and this background work, we know that oscillometry really is a potential tool to distinguish the relative contribution of bronchitis and emphysema. It's also important to think about why that might be. So when we think about bronchitis and emphysema and their spirometric findings and kind of the limitations of that, it's important to recognize that this is a forced maneuver. So both the bronchitis phenotype as well as emphysema are going to show airflow limitation organized by this low FEV1 FVC in both these groups. However, the mechanism by how that happens is different. In the bronchitis phenotype, we have more of an airway inflammation and airway narrowing. However, for the emphysema, we have more of a dynamic airway collapse that's happening during that forced maneuver that's leading to that airflow limitation. So the two very different kind of patient populations have kind of the same net result due to two very different mechanisms. So how can we further look at these groups and kind of change the parameters that we're testing under? So when we think about oscillometry, this is really performed under tidal breathing. So we know during our bronchitis group, we're still going to end up with that abnormal resistance and reactance shown by the Wada et al. Group back in 2018. But when we applied this to emphysema, they didn't have any specific correlation. There was something different going on there. The question is this different because we have minimal dynamic airway classes going on during tidal breathing? Is this a low elastin system? And might those emphysematous patients really actually have more normal tidal breathing? Could that be an explanation for the findings that had been seen in the Eclipse group, where there's a large proportion of patients that actually had those normal oscillometric findings? So given that, we had a couple of hypotheses. Specifically, we hypothesized that the relative contributions of parenchymal dysfunction, or emphysema, and airway disease, or bronchial wall thickening, will determine the pattern of abnormality that's seen on oscillometry. Additionally, we predict that the subjects with an emphysema predominance will demonstrate relatively normal respiratory mechanics as assessed by oscillometry, as this is during tidal breathing when that dynamic airway collapse is minimized. In order to test our theories, we retrospectively reviewed data from 23 patients that had a diagnosis of COPD who demonstrated hyperinflation. These patients were eventually subcategorized as either emphysema predominant or airway predominant based on CT imaging scores, which I'll explain further. Some prior studies have used quantitative CT to either characterize the airway wall thickness or the predominance of emphysema based on Hounsfield unit, which is a slightly different approach. So for each patient, we divided their lungs into 6 zones. There's the right upper, right middle, right lower, left upper, left middle, and left lower. Our radiologist then, based on some Fleischner Society guidelines as far as emphysema scoring, scored each one of these 6 different locations with a score going from 0 to 4, both for a score for how much emphysema was present, as well as separately a score for how much bronchial wall thickening was present. The bronchial wall thickening being suggestive of that more bronchitis phenotype. And then the total score for both emphysema and bronchial wall thickening for each patient was added up from those 6 zones, gave a score that ranged anywhere from 1 to 24. Now, given that this was a bit of a different method than has previously been used, we wanted to verify it with more objective physiologic data. And so in a subset of patients, 9 of the patients, we had recoil measurements from esophageal manometry that had previously been done. And we found that CT scan scoring supported correlation with physiologic parameters. You'll see the graph over here on our left. We've got recoil on our x-axis, and then we've got our CT bronchial wall thickening score on our y-axis. So notice that the recoil at the start of this is actually quite low and progresses more towards the normal value as that CT bronchial wall thickening score increases. Interestingly, you have that quite low recoil here at the beginning, suggesting that maybe there is, and most likely is, given that these are patients with COPD, some concomitant emphysema in those patients. And when we look at our emphysema score here, so once again, we've got recoil on our x-axis, and then our CT emphysema score on our y-axis. There's still a correlation, although in this case, it's a negative correlation, and it's not quite as strong statistically as our CT bronchial wall thickening score, but there's a clear trend that as the recoil increases, our CT emphysema score decreases. Think about this the other way. The more emphysema that there is, the less recoil that we expect to see. So given that we've kind of shown that our scoring system was effective based on some physiologic data, we wanted to look at oscillometric data and see if the relationships held. We found that emphysema negatively influences resistance. So here on our graph on our left, we'll start with the CT bronchial wall thickening score, and then we've got our R5 on the y-axis. Now, as the CT bronchial wall thickening score increases, the R5 roughly increases, but it's not a particularly strong correlation, and there's quite a spread on the data. And when we look at our graph on the right, our CT emphysema score increasing over here, and our R5 once again on the y-axis. There's a pretty strong negative correlation. That is, the CT emphysema score increases, the R5 decreases. However, there are still patients that have a relatively high CT emphysema score that still have an elevated R5. So again, is that going back to the interplay for a patient that they both have some bronchitis ongoing, as well as that more emphysema? It's really the interplay between the two of these that is going to lead to the trend for their oscillometric values. In order to test this for these patients, we went ahead and we calculated a emphysema to bronchial wall thickness ratio. So we took each patient's individual CT emphysema score as well as their CT bronchial wall thickness score and divided the emphysema score by bronchial wall thickness score. By doing this, we were able to subcategorize our patients. So those patients that we defined as being emphysema predominant were those that had a ratio of their CT emphysema score to their bronchial wall thickness score greater than 1, which was 9 of our patients. The airway predominant group, which ended up being 14 of our patients, were those patients that had a ratio of a CT emphysema score to bronchial wall thickness score less than or equal to 1. Looking at our overall kind of patient population, once we've divided them into these two different groups, the big takeaway that we want you to take from this big chart is that there are no significant differences from our between our two groups. In our emphysema predominant group as compared to our airway predominant group, we've got no significant difference in the age of the patients, the gender distribution, the exposures that they've had, the disease severity, the medication. And then from a physiologic perspective, during their forced maneuvers or the spirometric measurements, once again, there are no significant differences between these, no significant differences in the amount of hyperinflation present for those patients. We want to take, once again, that closer look at the oscillometric parameters for these patients. We ended up finding out that the resistance parameters remained near normal in emphysema predominant subjects. In our first graph over here on the left, we have our R5 on the y-axis, and then down here on the x-axis, we either have our airway predominant or our emphysema predominant patients. The airway predominant patients throughout are going to be in the white circles, and emphysema predominant patients throughout will be in the gray circles. We'll note here that the emphysema predominant patients have a normal R5 on average, whereas the airway predominant patients have that elevated R5. We look at the R5 minus 20. Once again, that relationship holds. Our airway predominant patients have an abnormal value, whereas our emphysema predominant patients have a normal or near normal value. When we look at reactants, once again, the reactance parameters remain within near normal in those emphysema predominant subjects. When we're looking at our reactance area here on our y-axis, in our airway predominant patients, this is significantly abnormal, whereas our emphysema predominant patients is near normal. And the same relationship holds for our reactants, that the airway predominant patients are abnormal, whereas our emphysema predominant patients are just about normal. So we take this one step further. We've looked at this in kind of a dichotomous fashion, more of a categorical variable, that patients are either, on one hand, they are airway predominant or they are emphysema predominant, and that's kind of the only distribution. So when we look at this on a more continuous way, we wanted to take a look at how the emphysema bronchial wall thickening ratio changes kind of over time, how that R5 would trend as the ratio continuously got bigger. And so what you'll see here on the first part of this graph is just our airway predominant group. Those patients that had the higher bronchial wall thickening score. You notice that there's not a particularly significant correlation in this group with that ratio that was less than 1. When we expand this out and we ended up getting our emphysema predominant group here, anyone that is scored greater than or equal to 1, you see that the R5 is normal or near normal regardless of how high that ratio gets. So it seems like it doesn't matter how strong that ratio is, it's seemingly as long as your emphysema predominant score, your emphysema score is higher than your bronchial wall thickening score, that is really kind of the driver of the oscillometric abnormalities, and that there really aren't significant abnormalities once you're emphysema predominant. And once again, that doesn't matter on the severity of how high the emphysema score was, just as long as it was higher than that bronchial wall thickening score. So given this, we came to the following conclusions. These findings indicate that once emphysema predominates, once again, that emphysema to bronchial wall thickening score is greater than 1, your oscillometric parameters tend to normalize regardless of the magnitude of airway disease present. Independent from the severity of airflow limitation on spirometry, the addition of the oscillometry to evaluate respiratory system mechanics could impact disease classification, prognosis, and potentially the therapeutic modality. And so just some kind of general thoughts that we'd love to have for discussion is what are really the mechanisms behind why this is happening? What happens after that ratio gets greater than 1? Is this just a high compliance system with low resistance? Is there some airway closure that's going on? Is it a balance of different lung zones that some have a higher impedance, whereas others have lower? Is this just related to a decrease in the overall lung recoil? Thank you for the references, and thank you. We'd love to have any questions or discussion.
Thank you, Bill. If you want to unshare your screen again. I'll start off with a question for you. Once again, lung volumes comes to my mind, and that is in the airway predominant patients, they have intrinsic airway disease, so you'd expect them to have higher airway resistance. The emphysema patients, let's say they were pure emphysema, no airway disease. I agree, at rest, their airways may be fully patent and resistance might be fine. But if they're also hyperinflated, then maybe any increase in resistance would be offset by that hyperinflation, whereas that may not be the case with the bronchial wall thickening people because their airway walls are thickened. They may not dilate as much due to hyperinflation. So I wonder if that could also be another mechanism on your last slide.
Yeah, no, absolutely. Yeah.
I see
We
Benno
have,
scratching his chin. What do you think?
Well, it's interesting, right? Because, and this is why we put that slide there for everybody to pitch in a certain way. Looking back, we look at the lung volumes and they're near identical. Everybody has very similar FRCs, very similar TLCs. So the plethysmographic structure of the lung, and I'm going to, again, highlight plethysmographic, which is what we would correct the oscillometry measurements to calculate the specific conductances, are pretty identical. That doesn't mean that that's what we're probing, right? When we put somebody on an oscillometer, I really don't know. What I find very interesting is that despite the big influence that airway narrowing would have on the impedance that we're measuring, as what nicely described, there seems to be this blunting effect, this quieting effect, that I don't care how much airway wall disease you have. The moment there is a balance of emphysema on that airway wall disease, +1, or call it whatever arbitrary number you want to choose in order to create a balance in favor for emphysema, all hell breaks loose. And what do I mean? We lose that signal. And every time that we look at a spirometry, we have an emphysematous patient, and we do these measurements in tandem. We take a look at the our oscillometry tracings. Patients with emphysema are absolutely almost undetectable. What is even more interesting is that the magnitude of emphysema doesn't tend to uber normalize or continue that downtrend as the destruction continues on a magnitude scale. So it just keeps on with the same level of normality, if you want to put it somehow. So I couldn't even, through that, try to come up with a mechanism to understand why two competing areas with differing impedances in lung zones, could explain what we're seeing. So I'm a little bit confused. I'll be very honest with you, and I just don't understand why we seem to have this blunting effect. From a clinical perspective, it's beautiful because I can utilize this to phenotype. From a physiological perspective, I'll just continue scratching my head until somebody who's smart can come and tell us or suggest some way to try to tease this out. I don't understand what is happening to these airways, and the lung volume doesn't seem to be it.
Thanks, Benno. Other questions? Charlie?
Well, I'll take a shot at it. I think Jimmy Hogg's work may provide you with an explanation. So what I understand the pathology of, or the pathogenesis rather, of emphysema is you start off with an neutrophilic inflammation around small airways. That's been well shown. And over a course of time, presumably due to the release of metalloproteinases and other enzymes, it basically cuts out that airway. So that airway is, it's like laser dissection. You just cut out that airway and then the surrounding tissue expand and pretty quickly you got a bullet. So one of the explanations for your work might be that in the early going, you're going to get increases in airway resistance, but then as the airways get dissected out and removed from the lung, the resistance falls. So in other words, the sick airways are being just deleted. And it's just that could easily explain what you're seeing.
With the reactants then not increase, well,
You buy that, Donna?
I don't know. I think it's very compelling. The amputation of airways that Charlie is mentioning, and which refers to Jim's work, could be an explanation. But if I stop counting those airways because they've eventually been destroyed, I'm left with either normal lung parenchyma or parenchyma with conducting airways that are sick. That's what's left.
Right.
And I would expect to see those. What I seem to see is that never mind how bad the airway disease that is present, whatever is happening with those disappearing airways and that parenchymal destruction evens out whatever impedance signal can be coming from the airway. And I can't explain it by disappearance. And I don't know, Charlie, it's still something that, I mean, might be so, but I just don't know that I see it.
I mean, the contribution of airway, I think our understanding of the contribution of airways from different generations of the lung is still pretty rudimentary. And most people would quote the famous paper by God, it's in every textbook, just showing that most of the airways resistance, central airways is on the periphery. And I'm not sure that's correct. It was done on 4 cadaverous lung measured at TLC. And what that has to do with airways resistance during mucus breathing, but I just don't think we really understand the relationship between structure and function as well as we think.
Hey, Ron, you had a question?
Yeah, I have a comment and 2 questions. I'm upset with you, Ben, because I thought I understood what was going on with emphysema and oscillometry. You've now stood me on my head. What I see in my practice with hundreds of patients that have been analyzed with quantitative CAT scanning is that we definitely get a frequency-dependent resistance, which worsens as the emphysema worsens. So, however, I'm not disputing what you're saying. Maybe we need to look at our data. Sometimes that's where it's most fruitful and we can understand, but then when you look at it, I want to ask you, why did you not use quantitative CAT scanning when the open source software is available by a slicer from Boston? You don't even have to pay for the commercial software. Why did you opt for the slicer sort of semi-subjective methodology?
So that's a great question. I'm not a radiologist. Our radiologist chose to do a quantification, which seems to be fairly well correlated with actual counting of Hounsfield units. I guess because we took a look at the analysis in retro, and got Elliot on board, which is our radiologist, and threw the kitchen sink at him. But you bring up a very valid point. At the end of the day, that's why we compare things with the esophageal manometer. I wanted to make sure that whatever he's calling emphysema, my goodness, has got low recoil, right? And when we saw the results, we're like, oh, okay, go ahead, use this. This is our little internal validation. And in a certain way, I skirted around the Hounsfield units by using good old physiology, right? And you're right. This is a little bit of a probe, if you want to put it somehow, a little provocation, but to do it right, probably in a prospective manner, counting emphysema in a uniform manner with Hounsfield units is the way to go.
Well, I have a couple of medical students who are quite adept at that, so get in touch, maybe we can help you out with that.
100%.
Come on up to Montreal or bring them down to New York. The other question I have, quite seriously, is do you know their alpha-1 status? Do you know if any of them are carrying the gene? What we think we're seeing here in Montreal is carrying either the S or the Z, for some reason is giving you less perturbation on oscillation mechanics than usual COPD. And so I think when you're reporting results, hey, my emphysema looks normal, the most important question is check their genetics.
100%.
That's interesting. All right, Phil, thank you so much for a very provocative talk. We really appreciate it. Thank you.
Thank you, everybody. Appreciate it.
All right, we'll move on to our next speaker, Paolo Medina from McGill, who's going to talk to us about oscillometry in adult CF.
Okay, so hey everybody, I'm Paulo. I am a first-year dentistry student at Montreal University, which I know is quite unusual within the context of the seminar. But I'll be presenting a study which I've been working on with Ron and Larry, otherwise known as Dr. Dandran and Dr. Lanz, in which we looked at spectral and intrabreath oscillometry in relation to spirometric impairment in adult cystic fibrosis. So cystic fibrosis transmembrane conductance regulator and modulator therapies have transformed cystic fibrosis care, with patients now having considerably better outcomes and improved quality of life. However, this has also called for the objective monitoring of treatment impact in lung function across time. But currently, the most commonly used test of lung function is spirometry, which is notoriously reliant on cooperation and strenuous effort from the patient's part, which makes it very difficult and oftentimes almost impossible in some specific populations, such as the very young, the elderly, the cognitively impaired, or the neuromuscularly weak. So we ran the study to see if oscillometry could provide an alternative and perhaps even a more robust evaluation of lung function. So I think this is the one audience where I don't need to explain in detail what oscillometry is, but I will say that we've used two types of oscillometry in the study: spectral oscillometry and intrabreath oscillometry, both being effort independent. However, to give a brief description of the differences, spectral oscillometry, it applies a composite signal at the airway opening containing various discrete signals ranging from, in our case, 5 to 37 hertz. In contrast, intrabreath oscillometry applies a single frequency signal, in our case 10 hertz, which allows for the monitoring of lung mechanics over the course of multiple breaths and over the course of time. So in other words, we can compute the following parameters. We can compute the resistance both at the end of an expiration and the end of an inspiration. And similarly, we can do the same thing with reactance and we get the parameters that are on the slide. So we hypothesized that both types of oscillometry would correlate as strongly as spirometry with cystic fibrosis health status metrics, and that oscillometry would reveal lung mechanical abnormalities when spirometry was normal in cystic fibrosis subjects. Through our methodology, we identified 60 subjects that were enrolled in the cystic fibrosis clinic in the Montreal Chest Institute that had the available cystic fibrosis health status metrics, which were the clinical, radiological, complication, and bacteriological scores, and that also had available biometrics, spirometry, and oscillometry data. Spirometry was performed at the PFT lab while respecting ATS criteria. Spectral oscillometry was reported through the use of 3 to 5 measurements while respecting ERS standards, and intrabreath oscillometry was reported through the use of 30 to 45 second measurements at 10 hertz. After some data processing, we classified subjects into either abnormal or normal spirometry groups. So subjects that had an FEV1% predicted of below 80% and an FEV1 over FVC ratio of below 70% were classified as having abnormal spirometry, and those that did not fit the criteria, of course, in normal spirometry. However, we also added a second layer of classification using spectral oscillometry. More specifically, we used the reactance area percent predicted parameter, which we set at a pretty conservative threshold for abnormality of 200%, since the comparison that I'll show later on in the results, to our knowledge, this is the first time this comparison was being made. Our final N was a 56 after we rejected 4 subjects, either for low reproducibility or extreme outlying data. So this table contains biometric data as well as the FEV1% predicted and the FEV1 over FOC ratio. Data is divided either into the entire 56 subjects or into the spirometrically split groups. The cells themselves contain the median of the data and the interquartile range within brackets. And on the far right are the p-values for either the Kruskal-Wallis test or the chi-square test, depending on the type of variable. And as can be seen by the mostly non-significant p-values, the data is pretty homogeneous across all. So on the slide, we have 2 heat maps annotated with on the top number being the Bonferroni-Corrente Spearman's row correlation coefficient, which whose magnitude represents the correlation strength, and on the bottom, the p-value for said coefficient. We focus only on the heat map on the left. We see the correlations between spectral oscillometry parameters and spirometry, the strongest of which being the absolute value of the reactance at 5 Hz and the absolute value of the FEV1, with a very strong correlation coefficient of 0.91. However, I will say that all of the spectral oscillometry parameters had at least one very strong correlation, which is at 0.8 with spirometry. Then on the right are the correlations between intrabreath parameters and the spirometric parameters. In this case, it was the and expiratory reactants, which had the strongest correlations with both the FEV1 and the MMEF absolute values. Here we have another heat map representing the same statistics. However, this time are the correlations between the cystic fibrosis health status metrics that I mentioned in their methodology, and heavily condensed because we've only included the 4 strongest parameters from each of the lung function tests. So from left to right, we have spirometry parameters, spectral, and on the far right is intrabreath oscillometry. If we go health metric by health metric, we'll start with clinical. The strongest correlation here was with the absolute value of the FEV1. However, the reactance parameters from intrabreath were not far behind, with 0.64 and 0.65 coming from intrabreath. All of these correlations being strong. Then for the radiological score, the strongest correlation came from the reactants at 5 Hz% predicted, with a coefficient of negative 0.67, which was actually the strongest correlation across the board from all 3 pulmonary tests. And finally, for the complication score, the strongest correlation came from the AX percent predicted with a coefficient of 0.55. However, once again, the reactance parameters from intrabreath were not far behind, having 0.54 and 0.53, which these are classified as moderately strong correlations. Finally, for the bacteriological score, all of the correlations across the board were either weak or very weak, and the p-values were non-significant. So like I mentioned at the beginning, 40 of the total subjects, which were 56, were considered to have abnormal spirometry. This comes out to 71% of the entire N. On the other hand, when we use our second system for classification using spectral oscillometry, we find that 49 subjects out of the total 56 had abnormal oscillometry, which comes out to 88% of the total N. Another way to look at this is through this box form plot, which on the x-axis we've divided into the spirometrically divided groups, and on the y-axis is the reactance area percent predicted. If we focus only on the box plot on the left, we see that 39 out of the 40 spirometrically abnormal subjects are above that red line. That red line is the threshold for abnormality in spectral oscillometry, which means that 98% of subjects that had abnormal spirometry also had abnormal oscillometry. What's more interesting is when we look at the plot on the right, where we see that out of the 16 subjects that had normal spirometry, 10 of those are above that 200% threshold, which comes out to 63% of the normal group, almost 2/3. So from these results, we concluded that both spectral and intrabreath oscillometry had strong to very strong correlations with spirometry. That spirometry in both types of oscillometry had moderate to strong correlations with cystic fibrosis health status metrics, and that spectral oscillometry was abnormal in 63% of those with normal oscillometry. And so a huge thank you to all the people on these two slides for making another study possible, and thank you.
Thank you, Paolo. That was really interesting, really great presentation. Are there questions from anyone?
Dr. from Rochester again. I was wondering if those 10 patients who had normal spirometry and abnormal oscillometry, did you happen to compare the clinical characteristics between that group and the rest of the patients? So the 10 of those patients had abnormal oscillometry but normal spirometry, do you happen to look at their clinical characteristics and how that compared to the rest of the group?
Just making sure by clinical characteristic, you mean biometric data or?
In that, I was just wondering if you took a closer look at that subgroup, the ones that those 10 that had the abnormal oscillometry but normal spirometry, like were they clinically different than the other 6 that didn't?
Patrick, that's a great question, but the answer is no. We just had the data. However, Arash Rad, who gathered all of that data just before COVID, is the guy who was actually seeing the patient in the context of research. And Stuart, who's sitting there 2 over from you, was supervising him at the time. And they probably didn't have really detailed access to the charts, I'm guessing. So the answer is probably no, but these are the 2 guys who could ask it definitively. They were kind enough to pass off the data. And this is actually comes back to a point that Ramon has been taking. It's really important for us to bank our data so that we can go back and look at it in retrospect. Because Arash had one objective in mind, which he accomplished, but bank the data, and then we could go mine that data with a second question, which is Paolo's project, which I think is the power of making sure that we acquire our data well and make it available to each other as we go forward. So that's my editorial comment, but I'll pass the floor over to Stuart and Arash to maybe answer your question.
We never looked at data that way. We do have a large now standardized CF database, but it would take a bit of time to do that. We actually had more than the 50 some odd patients here. And again, some of the clinical and other outcome parameters were not available when we did our original analysis. We have to go back and
I would like to ask a question. Well, actually make a comment. Charlie and I were chatting there. We were looking at all your data and realizing even though it looks like oscillometry is useful and actually maybe more sensitive than spirometry, for example, these 16 patients, nevertheless, FEV1 still pans out, doesn't it? Right?
It's a good test.
It's a good
It's
test.
a really good test. The problem is it's a pain in the butt to do.
Pain in the butt
That's
to
the
do,
problem.
agreed. But isn't it interesting that this arbitrary first second of exhalation seems to correlate so well with so many clinical outcomes?
Can I add a comment to that? Well, FEV1 is whole lung, almost, right? You know, for healthy people, it misses that last bit, but for very obstructed patients, the full 6 seconds is part of, well, the full maneuver, right? And oscillometry isn't. Oscillometry is FRC and a little bit above, you know, just where we're breathing. If we did oscillometry at different parts of the lung volume, maybe we'd find out more. Because oscillometry is proving to be a more sensitive measure at its lung volume.
Right.
Maybe it'd be even more at other lung volumes.
Well, we should get a move on before oscillometry is outlawed, because in my own practice, I have the spirometry rebellion going on.
Oh.
I'm not going to the torture chamber when you've got this in your office, doctor.
All right. Any questions online? I don't see anyone's hand up. If not, Paolo, thank you so much. That's great. All right, last presentation of the day. Oh, Dr. Urban. I'll just say it's my great honor to present Charlie. As many of you know, we've been working together for many years. In fact, I did my fellowship with Charlie way back in the day when we first described reversible. Yes. But it's all his fault that he turned me on to physiology. So this is but Charlie, it's a real pleasure to have you come up and talk about data from the LEAP study, actually, right?
Lead.
Lead.
Lead. Let's find the slide then. So first, I'm not going to thank Ron for being here because I wanted to come and not give a talk and enjoy it and be annoying. But I got forced into do this by him. I also get a prize for actually reading the stuff he sends us because I'm wearing the correct attire and the rest of them are not. I got involved more recently in this study from Austria, and I'm presenting today for my colleagues. Okay, this is, I'm not going to try to assume ownership of this in any shape or form. An extensive amount of funding went into this. I think they probably spent more time writing grants than working on the project. And if I mention the lung health cohort, this is a project David and I are involved with through the NIH. So there are gaps in our knowledge. We've talked about many of those. Most of the study with oscillometry have been done in people with disease, as we've seen. Understanding how it fits in objectifying respiratory symptoms is largely unstudied. And then more importantly, the prevalence of abnormal results in a general population. No, it's not. I can't share. I'm not sharing. I'm not going to. It's okay. Which is your talk here? That one. This one? No, it's over here. Irvin. See, cleverly named
study. Oh, it's not. I was looking for LEAP study.
No, it's LEAD.
There you go, Uncle Charlie.
You'd think after 50 years of dealing with physicians, I'd learn how to tolerate them more, but all right, so you've seen all that before. Whoops, I'm going. All right. All right, so the LEAD study had its initial focus looking at lung development and comorbidities. They assessed the locale, social economic status, genetic risks, and of course, with the hope that we'd identify risk factors in at-risk populations to study longitudinally. If you want to learn more about it, it's all written up in this paper. It's a longitudinal observational general population cohort design. These are really tricky to do. You have to randomize people into different bins. This is all done in Vienna, and I haven't been there yet. I plan to go, clearly. And it's been stratified by age, gender, residential area, male and females, wide range of age, 6 to 80, and over 10,000 people. I think the big thing here is that the questionnaires in terms of what disease the patient had and the respiratory symptoms are interview-based. But the classification of disease is self-report, and the plan is to follow them up at Q4 years. The aim of the current analysis is to determine in this general representative population the prevalence of abnormal oscillometry, its relationship to spirometry and association with respiratory symptoms. And the paper's been submitted, it's under review, and we're hopeful it'll get accepted for publication relatively soon. For this data analysis, we used all adult subjects above 18. We're using the Resmon Pro, one of the earlier versions. Remember, this was done some years ago so that the approach technically was based on what people thought was the best thing before the standards were written. We've been evaluating the data relative to 2 different data sets, although as we could probably discuss later, that could be problematic. These are the definitions of abnormal, diagnosis, self-report, and these are some of the criteria used in gathering the oscillometry data. Pretty standard stuff, really. This is the consort diagram. So there's 7,980 adult subjects with data.
420 were rejected because of low quality measurements. There were 40 that had zero resistance and 386 that had highly variable resistance at R5. And I'm tempted to think these might be vocal cord dysfunction patients, so we'll go back and have a look at them. This just shows the separation of the entire cohort, normal versus abnormal. If we use the two different equations of normality, there's only a reclassification of about 100 subjects. Not a heck of a lot of difference, although the people with abnormal oscillometry tended to be slightly older and just slightly heavier. I wouldn't call that, clinically a big deal. Now, this is the data set. And just to orient you to it, it's odds ratios here on the x-axis. This is the group of 5,400 who have no symptoms, nor do they claim they have a disease. You'll notice that the odds are actually left of 1, and that but there's abnormal parameter, any of the parameters used in 919 of them. So about 20% of normal people without symptoms will come into the clinic and you'll still get an abnormal result of some sort. Now, to show you one in the AX is much more likely to be abnormal than, and then respiratory resistance on expiration, and finally R5. And this probably is no surprise to any of us. But the other parameters can pop up as abnormal as well. Now, this next group is the 1,400 people that only have one respiratory symptom, no diagnosis of a disease. And you'll notice how they shift to the right quite markedly with just that. And again, the relative occurrence of abnormality is AX greater than resistance. This, I think, demonstrates in a very convincing way how sensitive this measurement can be. Now, at this point, you can't read any of this. It's too small. And this is where you get into the definition of big data, which becomes a big load for my poor brain. But what I've got here is no symptoms or disease, symptoms without disease, one symptoms, more than one symptoms, and then diagnosed disease. And what you notice is everything slides nicely to the right, so that there's a dose-dependent effect, if you will, of overall oscillometry measurements, abnormality. And this is where the comment I made earlier about it may not matter so much which parameter we actually choose. It's just that anything that's abnormal might be good enough. And that's where it comes out. And then again, AX tends to be the most frequently. The one that was kind of interesting is the inspiratory, expiratory, particularly within some of the disease subgroups, and end tidal flow limitation, which is very infrequent, but when it's there, the patients are very symptomatic, and any clinician knows that anyway. But that's nice because this sort of validates the approach in measuring what we think it measures. Okay, difference between disease, not disease, and its sensitivity. We conclude that subjects without symptoms or respiratory disease can present with abnormal oscillometry. They increase with number. As I just said, many with disease do not exhibit abnormalities in oscillometry. Okay, so just because we show this is a population-based thing, but there are going to be patients that aren't going to be different, although that remains to know what that means. So certainly in asthma, that's not surprising. Abnormal AX most frequently associated, whereas resistance at 5 Hertz didn't perform terribly well in this group. And then, as I already said, exhaled flow limitation on expiration is particularly striking. Now, this is broken out by the different, 3 different things: wheezing, breathlessness, and cough. And I think you can discern that they doesn't seem to kind of matter too much which one of those we actually looked at. It's the presence of one or the other. Here's the asthma, chronic bronchitis, and COPD is self-reported. And I think the striking thing was the inner breath differences between the two. Whereas COPD, you see big increases in expiratory resistance, not surprisingly, whereas less so in asthma. In fact, there, the inspiratory resistance tends to be worse, and we've already discussed that today, and I've told you what I think about that. This is now looking at another cut of the data, and these are the folks with normal spirometry. So their spirometry is normal, but in the general population without symptoms or disease, 16% are abnormal on one parameter, and you can read down how that increases with that. So that even in people who are normal spirometry, they can still exhibit abnormalities with oscillometry. And again, that shouldn't surprise this crowd terribly much. And we saw that this just confirms the ability of oscillometry to pick up abnormalities. So in summary, as far as I know, this is the largest epidemiologically based study where the subjects were collected in a very randomized representative way. Abnormalities are important, about 20%. I'll comment about that in a minute. And each one of the symptoms, even one symptom, increased the prevalence. We know that OS is basically dose-dependent, or I sort of said that. And even when spirometry is within normal limits, you can still see abnormal oscillometry, although keep in mind, this is also seen in people without apparent disease or problems. And I think this, I've seen this before when we've looked at rhinosinusitis in patients and normals, and we're seeing it in our lung health cohort as well with CT scans, that if you take normal people and start studying, you find a lot of abnormalities, and that's just sort of the background noise. In the one study with sinusitis, we threw the CT scans out in terms of ability to discern whether a person had rhinosinusitis or not because of the increased, the high prevalence of opacities in the sinuses in people that apparently have no disease. Oops, hit the wrong thing. All right. We conclude, shock of shocks, that underscore the value of integrating oscillometry and routine respiratory assessments, particularly in patients with or individuals with preserved spirometry. These are the investigators, and I'm hoping that some of my colleagues are actually online. In case you ask some hard question, I'll just ask them to answer it for me. This is a true international study: Italy, Austria, the Netherlands, United States. And of course, we thank all our participants for giving of their time to be involved in a really important study like this, our funding agencies, and everybody else who matters. And then questions.
Thanks, Charlie. Any questions from anyone?
Charlie, it's been 48 years. Framingham linked the NBC cardiovascular mortality.
Don't start me.
Is this like oscillometry's Framingham?
It might be. I think we started the lung health cohort because there had never been well, this one now, which is they're ahead of us in that sense. Studies that have actually looked at the longitudinal development of lung disease in a general population. It's not known. We know it for other diseases. I mean, the cardiologists convinced everybody to do that decades and decades I actually maintain, and I hope nobody's recording this because I'll get in trouble. I think the biggest setback to pulmonary research, certainly in the United States, is NHLBI. The fact that the lung folks got sucked into the heart. Okay. Because I've been on these study sections and the cardiologists just drive everything. One of you talked about maybe it's not time to add oscillometry, and I say if we were surgeons or cardiologists, we would have been using it for 20 years already. But they don't seem to be hung up with the kinds of things that hang us up. We're much too discerning, I think, and we just got to kind of go out and do it, find out how it really performs. And I think our comment about spirometry, how just time and time again, it pops up as being a great test. It's a pain in the ass to do. Is oscillometry really the same thing? And will it perform the same? Will it predict death? What does it mean, by the way, if in all these 20% of people who have abnormal oscillometry, will that predict it in 20 or 30 years?
You've got the data now.
Yeah, but I'll be dead.
By the end, you're 5 years elapsed.
Yeah.
5 and a 10-year follow-up.
Well, their plan is to do 4, and our plan is to do 5. David and I wrote a grant for our lung health corps, but we're only going to measure oscillometry in 1,000 people if we ever get the ball rolling. But we will have CT scans, and we'll be measuring some different things than the lead study because we all have different. We look through the world.
We'll have
with
LCI. Now, the fly in the gun is that this is no longer the largest study.
No, I
The
know.
world is changing. So one of Leonard's friends out of Uppsala, or is Marlborough,
It's both.
they have 10,000 patients, which is out in the ERJ open.
Yeah, well, there's 10,000 in this too.
Yeah,
The
but
kids just aren't in this subset.
Yeah, but they're reporting, and their results are the opposite. Spirometry more prevalent than oscillometry, but there's fundamental differences in how the studies were set up.
Yeah.
They're a narrow slice. They have a 10 or maybe 15-year window of age. So it's not the same spectrum.
No.
And their definition of normal is they took those who were normal in their study by their assessment and derived their own normative data. So their definition of normal and abnormal oscillometry is different from everybody else so far. I had invited them to come and talk either ahead or behind you, which would have been great in this venue. However, the hammock was calling and Sweden is on holiday.
It was Finland, the crawfish.
No, and actually, if I don't remember wrong, because they use the iOS, and depending on how you set up that machine, you're not going to save the raw data, so you can't go back and reanalyze.
No.
And so
You
they never collected AX, for example.
No.
The other things. So they might have had a signal had they collected all the possible data.
Yeah. So I wanted actually to have these differences in the studies pointed out because the problem is the clinicians who are less facile with oscillometry are going to get hold of it and say, see, I told you, not ready for prime time.
Yeah, it's, just going back to the two sets of data that are used for predicting normals, both Ellie's data and Penn's. I mean, they're very different. Instruments are different sites, and they're small studies. They're 300, 400. I mean, if nothing else, we can take the 6,000 or so people and do them across the age span for both, from 6 all the way to 80. That would be incredibly valuable, I think.
But you made the point, and it was, I don't think, emphasized enough. You looked at the data in the leads, with both sets of normative data, whether you used Ken's data from New York or the multi-center older set.
It didn't
by
change
only
only about
the
100.
same by 1%. And so for
Yeah.
me, the silent zone is screening 7%.
Yeah, and anybody who does this work, you know, when you look at, for those of us who run lung or did run lung function labs, and you look at different equations, there's actually a lot of difference between the various ones. And I think only 100 patient reclassification for a data set this size is really tells me that, you know, in spite of all these things that we shoot at this, that it's a pretty robust measurement. And then David and I've been involved with documents about the role of race, which is a very sensitive issue. And wouldn't it be wonderful if we didn't find a heck of a lot of difference between races by using this technique? That would be a major step forward. So, yeah.
Oh, yeah. I was just wondering, I mean, I think that you may have insight into this too, like even though you're not a clinician, you have so much experience, but I was wondering on the practicality of it, like as you were seeing patients in clinic, do you like give them a report? Do you put it in as kind of a point of care test? Like how are you kind of using it right now? Like,
All of my asthmatics, every visit, they have their ACQ and they have their AX is in particular recorded in the chart, and that's what I track. Although I look at the whole oscillogram is there, and that's since COVID. Before COVID, they all had spirometry on every visit, but post COVID, when I opened up, I just switched over because I had been convinced. So I've made the switch. My COPD patients get it once a year, along with their full PFTs, but it's also included in the chart. And I'll sometimes believe I can make medication switches based on localizing as either predominantly small airway or non, in terms of choosing the particle size. Some of us that believe that particle size matters, and then 2 microns ultrafine will go more evenly to the small airways and more peripherally. So I'm using that clinically. Whether that's right or wrong is for people with bigger budgets than I have to figure out, but it seems to be working for me so far. I'm comfortable with it. And as I said, my patients love it because they hate spirometry.
how is that in buy-in from what, or respiratory therapists, or you know, who's doing the testing?
Turn around and ask them directly.
Oh yeah.
Ladies.
Hello. Oh yeah. I was wondering how you
Wendy?
can hospital or
Ask them.
personnel backup, yeah, to do all of this testing, because you're doing this on.
Stephanie and Wendy are very experienced with oscillometry. Their RTs are the equivalent of what you have for doing lung function in the States. And they should express their point of view here.
Yeah, I guess, I mean, like in terms of workload, like when I bring this up to our PFT lab, I feel like our RTs may quit if I try to throw FOT onto them, like in terms of a billable or, you know, billable kind of procedure.
Well, I'll let them respond, but I have a comment.
We have clientele that are very severe in their disease, and it is difficult for them to perform normal spirometry. Once you've got your respiratory therapist trained, as Dr. Nanduran did, trainings and, you know, formation, so people know what they can do, and then you let them practice, they will see for themselves that it's much easier.
Right.
And then for the patients, they can perform it. Yeah.
Right.
So, and it's not taking more time. It is very effective. So, that.
But has your workload overall increased? Because some people may still be getting an annual PFT plus this.
Yeah, but
you know, like
the way the schedule is made, it's not making things more. It is not increasing more. It is one patient instead of another one. And PFT wise, usually the same lab. PFT will take 45 minutes. Oscillometry.
Yeah.
So.
So we started off with one community hospital, and then the Veterans Hospital, and then we have 2 more community hospitals asked to buy in. They're asking, can you please set us up with oscillometry? So now their RTs and our RTs are coming together and training each other, doing in services, and now so we're deploying it over, you know, probably the western third of the island of Montreal. And in parallel to that, we're doing something on the East End. So Montreal is going to end up being an early adopter. The question is whether we make the switch before or after. It's hard to do anything until the guidelines change. And then in parallel with that, of course, the billing code.
So David and I have been involved with training our coordinators from over 30 centers across the United States, and they're very enthusiastic about this technique relative to other things that they do. One of my colleagues, the first author of the paper that I just presented, Professor Venneroni, is online. I was wondering if you had any other additional comments to make. Well, I called her out. I hope.
Yes. Thank you for giving me this opportunity.
Oh, there we go.
I'm not alone. Actually, I think you did a pretty good job, Charlie, and I have nothing.
Oh, good.
special
You're not
to
going to get mad at me. Excellent.
No, no.
So if it was a good job, they get the credit. If it's a bad job, I was going to take the pain. And she was telling me she just was on holiday, but she didn't get much relief because of the little ones. And I could see what she's talking about.
Ramon had a question for you, Charlie. Ramon, are you on?
Oh, Ramon, sorry. Hola.
Okay. Yes, this is not a question, it's a comment or a reflection. So I think that this nice presentation with thousands of people involved show one thing, is that most or many of the parameters we use to characterize respiratory mechanics by oscillometry are redundant. So most of us, or many of us, come from the field of physiology or pathophysiology, where we want to have a very comprehensive and extensive description of the system. We like to play with a lot of frequencies, a lot of parameters, and so on, which is good, because as many parameters we have, we may better understand the topic. But from the point of view of a clinical acceptance of the technique, as much of parameters we use is a problem for clinicians. The clinicians like as few parameters as possible. So my question is, this study shows very nicely what other studies show, and also many results show today, that in reality, probably 1, 2, perhaps 3 parameters may explain most of the information about the respiratory system in different diseases. So my question is, or my reflection is, we should, in my opinion, try to reduce ourselves about the complexity of parameters. We have to try to distillate the information to have at the end 1, 2, 3 parameters at most that we can provide to the clinical field as useful tools. So I don't know how to do that, and whether you agree in general, but this is my impression.
Yeah, I violently agree with you. I think we, as physiologists in particular, and I'm guilty of it as anybody, we really like getting into the nitty-gritty and talking about it. But then that's one of the reasons we don't use spirometry in clinical practice anywhere close to much. We've shrouded it in all this mystery, and I don't think we need to. Again, it doesn't seem to bother the cardiologist to measure blood pressure, which we know is an absolutely terrible measurement. And yet every time I go in the clinic, they measure it 10 times. I go get my glasses thought of they're measuring it. And I think that, just simple impedance X or admittance might be more than adequate for things. Because when you think about it, the average person wants to know, is there or is there not a problem? Well, one parameter here would have gotten you there. How bad is it? Well, we know that the worse it gets, the higher it gets. So it's 2 of the most important questions you want clinically are answered. And the only one that's really left is, if we make a lot of these measurements, will we learn something really peculiarly interesting about the patient that said our diagnosis was wrong or our treatment should be different? And that's where we're hopeful that something will come out of that. But I don't know. The more I think about it, And typically this seminar has caused me to think about it even more. I don't think it really matters that much. And while we might be fascinated about it, we should not let this hold us up from introducing this into clinical practice, because now's the time to do it.
I just wanted to add, I'm sorry, I don't know.
Oh, sorry, Silpa.
Silva. To add to what Stephanie was mentioning, I work what is considered, used to be considered the Veterans Hospital. And sometimes there would be a diagnosis of COPD in the chart, but was never tested.
Right.
But some of our gentlemen or our ladies, they were like in their 90s, and we just couldn't get them to do reproducible, 3 times. It just wasn't possible. They were too tired. And so when oscillometry was introduced, they were happy. We were happy too, because we're doing a test with them, and we could see the fatigue that was setting in. And so
yeah, I'm getting to the age where I don't want to do spirometry. So I know where they're coming from.
It helps in some patients. Like I once had a referral of a patient like from California who was billed to me as severe deployment lung disease, going to need a lung transplant. And when he came, National Jewish, we did some multi-day evaluation on him. So I was able to add in oscillometry in addition to everything else. And I was like, this guy just can't do taking in a deep breath. He would just start coughing on inspiration. I was like, he just has crappy spiro. Stop doing spiro. And that kind of made sense with all the other clinical picture. He did have lung disease, but it wasn't like a death's door. The oscillometry helped us.
Well, we could actually push the age envelope. I was getting ready to run a big trial when I was at National Jewish with kids. And we found it, I had some of the techs bring in their kiddies into the lab. I found that, a 2-year-old, you can get a 2-year-old to do this. In fact, they liked it. The one kid would run up and down the hallway and come back in and plop down and go, oscillate me. So, I mean, some people find it actually kind of a lot of fun.
The pediatric allergists at National Jewish have really adopted it.
Yeah.
Nathan Rabinovich, I think, has taken that one
Yeah,
up there.
yeah,
But the pulmonologists have been slower.
I think kids will get into this. Just saying.
No, the Children's Hospital in Denver, they have tons of oscillometry.
Yeah.
Yeah.
Well, Charlie, how about we go get a beer?
I think that's a good, you're buying us some beers, because I didn't want to do this talk and I didn't want to wear this shirt. All right.
I think this is an important study to get out, and this would be a perfect diving board to jump off of into our Sanka set, our networking cocktail and supper, because we have a lot to talk about and share. Thank you, everybody, for a wonderful day. And 9 o'clock tomorrow morning, we'll pick up where we left off. But let's go have a good time right now. All of you out on the interweb, have yourselves a good evening, good night, and we'll see you again tomorrow. Bye-bye. Bye, Jolie.